Jeff? I would be.
Okay, I have a poster. What I like to do is, are you gonna have time for people to give a 1-minute poster?
That is not scheduled at this point. I'm sorry. You can talk to the chair.
That can be part of the second session.
I don't see it on the schedule anywhere here. Poster pops were not included as near as I can tell. Sorry.
Okay.
Yep. Okay. Hello, is this on? Okay, great. I guess it is. Hi, I'm Andrew St. Georgi from the Harvard Smithsonian Center for Astrophysics, and you're in IAUS 393, Planetary Science and Exoplanets in the Era of the James Webb Space Telescope. Before we get rolling here, our chair of this session, Zuhair Ben-Khaldun, would like to say a few introductory words, and I'll give him the mic.
Yes, thank you everybody for coming. We are very happy to make this symposia possible, and we organize it here in Cape Town. But I would like to thank our colleague from both division F and C for their endorsement of this symposium. Indeed, the idea of this symposium was first discussed within Arab Astronomical Society, and we plan first to organize it in Marrakesh, Morocco, due to exciting development of exoplanet research, in particular in Morocco. But due to postpone launch of James Webb Space Telescope, we decided to postpone twice this symposium and align it with the General Assembly. So allow me, in addition to thanking, of course, the effort of both two committees, SOC and LOC, for this symposium, to give a special shout out to my friends at Arab Astronomical Society, who are doing an excellent job for developing astronomy in the region and supporting young scientists by organizing a regional school in particular. So thank you, Andy.
Thanks so much for those words of introduction. Just a quick thing to the speakers. There's this indicator here. When the green light is on, please give your talk. When the yellow light goes on, please take questions. And when the red light goes on, you've been bad. So with that caution, I'd like to introduce our first speaker, Nicole Colon, who will be talking about the dawn of a new era for exoplanet detection and characterization with JWST.
Thank you so much. All right, it's great to be here. Okay, looks like my slides are up. So first I wanted to start and thank the organizers for having me here today to talk about this. This topic, I work at NASA Goddard Space Flight Center, and I'm currently the JWST Operations Project Scientist. I also want to acknowledge and honor the land that we stand on here today in the African continent. It's my first time here, and I'm really grateful for the opportunity and grateful for everyone hosting this conference here. So I wanted to start by saying, of course, JWST doesn't just do exoplanets. So I have a lot of non-exoplanet pictures on my title slide, just to showcase, this is a very powerful observatory. And, since I'm the first talk of this session as well, I wanted to start with some big picture topics and then dive in to some themes that we're seeing in exoplanet results in the past few years. But so with JWST, of course, it's a very powerful infrared telescope. It's 6.5 meter size, also enables it to see things at higher precision and, with more power than ever before. And so the core science themes of JWST are shown here. Other worlds, exoplanets, disks, solar system, planets as well are all in this category, which is only, of course, one part of the science portfolio. But it's still a major part. And that's the great thing about the observatory is that we can study this. We can study these other worlds to learn about different properties, answer some of these key questions. How do planets form and migrate within disks? What is the composition of exoplanets and their atmospheres? How does the star affect planet formation and evolution? And even start to touch on the idea of whether Earth-like planets are common or rare. Again, JWST wasn't necessarily designed to study, Earth-like planets around sun-like stars, but as I'll touch on, we're of course, working on the challenge of studying small rocky planets because there are many of them. And so with JWST, I might be saying things you already know here, but I just wanted to emphasize that with its 4 science instruments, we have a lot of capabilities with this observatory, and there's 17 unique observing modes, and many of them are useful for exoplanet science, ranging from imaging to spectroscopy. And so again, pushing into the infrared where a lot of exoplanets hadn't been observed before or had only sparse data with the Spitzer Space Telescope, for example. And so with JWST, let's see if my slide advances. Okay, I don't know if these movies will play, but it's just the standard animations showing what happens with direct imaging. With JWST, we mainly use coronography to block out the light from the central star and to reveal a faint planet around it. But we also use the transit method, and it looks like the animation didn't play, but I think you get the idea of the planet crosses in front of the star, and you end up seeing the planet plus its atmosphere, if it has one, blocks some extra light. Oh, there you go. Thank you. And so with this opportunity with transiting planets, we get to study the atmospheric composition, chemistry, structure, and similarly with direct imaging. So of course, these are the main ways we study exoplanets. I will note I'm not talking about disks in this talk, but I know we have some talks later in this symposium on that topic. I just didn't have time to cover it, but that's also a big part of the story, obviously, with exoplanets. But so just to emphasize finally here, why we use JWST, of course, is because the infrared is especially a powerful wavelength to probe the deeper atmosphere of a planet. And we want to capture or measure abundances of carbon molecules, in particular, carbon monoxide, dioxide, methane, also things like ammonia. All of that gives us the basic abundances of things like carbon and oxygen and hydrogen in the atmosphere, which really helps tie to formation of planets. And so that's one great reason to be in the infrared, but also we get to probe, as shown in the diagram here, different facets of the atmosphere, like thermal inversions, the presence of clouds and hazes and the composition of those as well, and other atmospheric features like circulation and chemistry processes. And so I just have one slide on pre-JWST state-of-the-art. Hubble and Spitzer provided a lot of state-of-the-art of atmospheric observations, along with many ground-based observatories as well. But so this was kind of a the best case, one of the best cases, let's say, we had of exoplanet atmospheres before JWST, where you see the yellow data points are showing, again, the amount of light blocked from a star or from a planet in front of its star versus wavelength. And you see a lot of the bumps and wiggles indicating water, also water absorption, but also some alkali metals, sodium and potassium. And then there's a hint in the Spitzer band passes around, between 3 and 5 micron, a hint of carbon dioxide. But so I just wanted to start here because I feel like I have to start at the beginning. This is kind of old news now that JWST detected carbon dioxide in a gas giant, but this was really important. This is one of the first results kind of out of the box. Firstly, that you have, a transit, and this is, again, real data, not simulated. It's just that good, right? You're seeing real transit data. And then when you break it down as a function of wavelength, you get to see the carbon dioxide feature just jump out at you. And that's really exciting because, again, with Spitzer, we could only often get those 2 data points that didn't, resolve the feature. And so this was just a beautiful result to start off with. And so if you didn't, believe the power, I like to show this graphic too from Hannah Wakeford, comparing the Webb and Spitzer data and just showing how we resolved that feature wonderfully. But of course, this was just the beginning. So since then, there's been, a plethora of molecules detected with this observatory for transiting gas giants. And so I included, a bunch of examples here and several references as well. This is not an exhaustive list. There's many more papers out there, but I just wanted to point out the things that JWST is providing us are, many of them are expected, right? We are getting the carbon molecules. So all of them, I wonder, oh yeah, perfect, I have a laser. So up here you see the colors are indicating the different molecules detected in this planet. This is WASP 107b. And so this is a zoom in of JWST NIRCam data here. And so, for example, this is the big carbon dioxide feature, and then you have a MIRI data here. And the yellow, I want to point out, shows the SO2 feature, which is a byproduct of photochemistry. And so we'd seen this first in the Hot Jupiter WASP 39b, but since that first discovery, SO2 has been seen in several more planets, which is great that, a lot of times we're seeing this even with one transit observation, it's just kind of jumping out at us. And that's really exciting to see. Again, now we have direct evidence of something else happening in the atmosphere, this chemical process. And among other, features, there's methane, example also in K218b, which is, depending on who you ask, it's either super Earth or mini Neptune, but it's there's methane is a key of disequilibrium chemistry. And so that's another good molecule to detect. We've been searching for it for a while, is expected to be in cooler planets, and we're finally seeing that with JWST. And then we even see more exotic features like quartz clouds in this WASP 17b. So this SiO2 bump up here is indicative of clouds made of quartz crystals in the atmosphere. And so these are the kinds of things that we can learn, the molecules and all that, but we're also learning about the structure and of the atmospheres. So not just molecules and chemistry, but, in a way, physical structure, because we're seeing things like asymmetries in the data. And so these are, again, just a couple examples for transiting giant planets where we see, as an example, so when you have a planet transiting in front of its star, you have a morning limb and evening limb, essentially, around the terminator region. And this paper by Espinoza et al., you see differences in the spectra. That's the blue versus red here. And so it's telling us, that, again, we're seeing differences here in the atmosphere between, well, there's a day side and a night side firstly, but these are actually relatively cool gas giants. This type of asymmetry, I believe, has been seen for ultra hot gas giants before. But so I think maybe it wasn't necessarily as expected in cooler giants. So that's the interesting part here, is seeing the inhomogeneities in different types of planets now, different classes of planets. And then similarly here, this is the orbital phase curve of the planet WASP 43b. And so this is when it goes behind its star, and then in front is actually cut off here. But what you can get is a map of the planet. Basically, its temperature, and you can measure the hot spot of the planet. Again, we're assuming tidally locked. These are mostly all tidally locked. And so it's kind of hard to see by eye, but there's actually a little, it's kind of offset from zero here. And so we're seeing a latitudinal asymmetry in the hotspot of this planet. And that was something, fresh that JWST was able to provide us as well. So we're getting to learn a lot about giant planets with JWST, and going back to kind of the composition, the carbon and oxygen ratio in particular. This is a kind of diagram we can start to make and put together to understand the formation and evolution of planets. And so this comes from a paper by Kempton and Knudsen. And you can see this is kind of broken up carbon oxygen ratio versus metallicity. And this actually includes not just JWST data, but also ground-based data as well. But so what we can do is start to populate different regions of the diagram that indicate, you know, if a planet kind of falls in this diagram, in this part of the diagram, it might have been more likely to be subject to disk migration, plus, you know, accretion, a lot of accretion of icy solids during its formation. And so we can start to do this, you know, by measuring, again, those carbon molecules in the atmospheres, which is really possible, you know, from the ground with the hottest planets, and then now with JWST for more types of planets. But we also study smaller planets, right? And so I talked a lot about giant planets. That's where we've gained a lot of information so far. But a lot of small planets are being targeted with JWST as well. A lot of, you know, super Earth to Earth-sized planets. And so these are just two examples shown here. Again, not an exhaustive list at all of the papers out on small planets. But I wanted to show this because this is kind of a typical example of what we're seeing is you have, you know, your JWST spectrum here. And it basically, often they are flat lines, but what that does is it helps us rule out a lot of these models behind the data here that are indicative of, you know, hydrogen-dominated atmospheres, something else called a Haitian world. We can talk about that later if you want. But the point is, when you can rule these out, that is quite helpful because then you say, okay, well, what, you know, could be a better match to the data, you know, even though it's a flat line, at least right now with JWST. And so something like, you know, nitrogen or carbon dioxide dominated atmospheres in this case, you know, have much smaller amplitudes in the models. And so, you know, I want to stress here too, the scale. This is only, you know, looking at tens of parts per million here, like the error bars here, but of course the features are much smaller than that. And so when we study these small planets, you know, we can rule out the fluffier hydrogen dominated atmospheres that are, you know, shown in some of these like yellow and green models and all that. But we have to keep pushing to the highest precisions to keep getting down, you know, to roll out more and more models, if not detecting actual atmospheric constituents. So one thing we need is the highest precision, which is a challenge. These things are small, their atmospheres are thin, not really surprising. But then also something else we can do shown on the other side here is the TRAPPIST-1c, which some have postulated maybe it's a Venus-like planet with a Venus-like atmosphere. But this data is actually from when the planet goes behind its star. And it also essentially rules out where this data point falls. It rules out a Venus-like atmosphere for this planet, and so it likely either has no atmosphere or no thick atmosphere. And so that's kind of the trend we're seeing with these planets. But added to that was host star activity. And so I just wanted to point out briefly that, you know, all the stars, or many of the stars that the small planets are transiting that we're studying orbit K and M stars. And this is Mercury in front of the sun, but it's an example, you know, again, to show stars are not uniform, right? They have spots or faculae, just inhomogeneous surfaces. And so when you have a small planet transiting a star that's not uniform, these things can affect the stellar surface inhomogeneities can affect the detection of the small planet atmosphere that you're chasing. And so this was one example of that. But there have been others where a team got data with, I believe this is a near spec instrument of this super Earth GJ 486b. And you see out here, the data kind of matches two models, but then the two models, one of them is for a situation where there's unocculted star spots, but the planet has no atmosphere. That's the orange model. Or there's a model in blue where the planet has the atmosphere, but it's indistinguishable at this wavelength. So of course, one thing you could do is get more data out here, right, to distinguish between the two models. But it's still a general challenge moving forward with all these small stars, because JWST is actually revealing even some stars that were thought to be quiet and not active. We're seeing like spot crossing events in the transits. So a lot of the stars are active. And so I just wanted to touch on this here, that there are several programs going on to tackle this problem with these cool active host stars. And this is a neat one targeting the temperate planet TRAPPIST-1e. So it just started a couple weeks ago, I guess. It's a cycle 3 and 4 program. And so it's led by Natalie Allen and Nestor Espinoza. And it's looking at transits of TRAPPIST-1e, but this is a 7-planet system. There are many transits of all the TRAPPIST-1 planets like all the time. And so what the team cleverly did was propose to observe basically back-to-back transits of TRAPPIST-1e and b. This is all simulated data. But the idea is that, they transit close to similar chords of the star. And then again, simulated data, assuming planet B, it's the innermost planet, and there's also been papers out there that saying it likely doesn't have an atmosphere. So assuming it doesn't have an atmosphere, if you use planet B, and you have planet E at the, basically the same time, you can ratio those out because they're covering the same part of the star. And so hopefully what you're left with ultimately is a true spectrum of planet E, because removing planet B from the picture helps take care of the stellar effects that you aren't necessarily able to sample, if there's unocculted star spots and things like that affecting your data. But so it's a pretty clever way to try to get around this stellar contamination effect. You can't do this with, all planets, of course. Not all of them are in multiple planet systems like this. But hopefully the idea is to get, detection of carbon dioxide if there's an atmosphere around TRAPPIST-1e, but it's going to take a while. This program extends into cycle 4, so I believe its observations are scheduled through like 2026. So, stay tuned for results on that. But I thought that was an interesting thing to bring up. But so that was a bit of a whirlwind tour of transit results so far. But I also wanted to touch on direct imaging before I wrap up, because with direct imaging, I feel like there's a lot of talk of other observatories. Of course, the Nancy Grace Roman Space Telescope will have a technology demonstration with its coronagraph. And then the Habitable Worlds Observatory, which we'll hear a talk on later, will be designed to directly detect Earth sized planets around sun-like stars with coronagraphy. But JWST is also doing direct imaging and making great strides in this area. So just to start off with, this was one of the first results that came out. Just emphasizing, again, we didn't have many planets detected at 5 microns or beyond before JWST. And so this was a great result, seeing the planet here with NIRCam and different MIRI filters. And this first demonstration also showed that JWST was exceeding its performance requirements by something like a factor of 10. So it's doing quite well with its direct imaging here. But beyond that, so that was a previously discovered planet. So it was, a test of something that already been discovered in the past. And so other direct imaging programs, though, have attempted to search for new planets that hadn't been discovered yet. And this is one example of a program that looked at the Orion Nebula and the trapezium cluster. And so here's, part of the nebula here and 2 different filters. And then these are some well-known disks that were sampled, which, look beautiful also. But the thing that caught my eye was in the paper, there's all these tiny little dots here, if you can see, right in the middle. And basically this team was, doing high resolution images of this region and found something like, 540 planetary mass candidates down to, I think, 0.6 Jupiter masses was the lowest estimate. But so many of them were in binaries, like you see a lot, or I think all of these examples are binaries, like binary planet mass objects, not stars. And so this was pretty surprising to find so many just kind of potentially, I guess, free-floating planet candidates hanging out there. And so this is really intriguing. And so I'm curious to see, what else comes out of JWST observations in the future. In, I guess, nebulae and other cluster regions as well. But this was also an interesting result that came out with direct imaging, looking at white dwarfs. And so here's two different white dwarfs shown on the left. And you can see this is with the white dwarf. And then after you subtract the white dwarf, you have a faint little dot here, and then a faint dot here. And then that's considered a candidate planet. And then if you, model that and subtract that out, you see it does subtract out nicely. This up here is a nearby, or not a nearby, but like a background galaxy. But so this paper presented these two candidate giant planets around this white dwarfs. And the interesting thing was that, as it says at the top there, these were at separations similar to giant planets in our own solar system. So, could it be that they survived, again, the end stage of evolution? And what does that mean for, the evolution of other planets around sun-like stars? Could giant planets at least survive? And so this is really exciting to see, and I think there's more observations coming, or at least proposed for, to follow these up. And then one final direct imaging result that came out recently, not final, there's many more other results, but this was one of the most recent ones that came out on Epsilon Indi AB. So this was discovered originally with radial velocity detection method, but it was subsequently directly imaged with JWST, just announced a few weeks ago. So it's, if you kind of look at this, at first it might look like a simulation, but this is actually a real, direct detection of a planet, of the planet. Although my understanding is the team that led the discovery, the planet was, I think, a little further out than they thought compared to the radial velocities, period. And maybe, and so therefore a little colder, but I think it's one of the coldest planets ever detected directly in the first place. It was detected with MIRI in this case. But it's also just, again, showing the power of JWST, like, when we're in the infrared, we can do these things that are really, kind of fun, and follow up on these long-term radial velocity discoveries that have been looking at planets for decades now, and we can start to look for them in direct imaging and actually make, direct detections and study their atmospheres. So that's really fun. Okay, so I think I'm almost wrapping up here. And so I wanted to, so again, that was a whirlwind tour of direct imaging results, not all of them, again, not exhaustive, just want to emphasize that. But I wanted to highlight a couple other things. This is a fun tool. If you haven't checked it out, you can see what JWST is observing now. I took this screenshot a couple months ago, back when it was observing this target K222b. There's other planets that are being observed with this telescope. Of course, I talked about transiting planets, giant, small planets, direct imaging, all that. But there's even more fun things that are ongoing in the works. This planet in particular is disintegrating. And so the goal of this program, for example, is to study the interior of the planet and look at the rocky material that is literally, disintegrating off of the core of the planet, and measuring the composition and seeing, what we can gain from that, using some MIRI orbital phase curves. And so that works in prep, but that's just one other example of a different type of observation that you can do with JWST. And then if you hadn't gotten the notice, I have to do, due diligence and announce the next round of proposals is open, So obviously every year there's more and more to come. This next cycle just opened. And I wanted to point out too, which actually, yeah, it does say here, the number of hours available in this cycle has increased drastically from previous years. So, definitely put in your proposals if you have an idea. When I mentioned at the beginning, the science themes of the observatory, they're broken out, and one of them is other worlds, but also the the proposals that get selected all come down to proposal pressure too, the topics of proposals. So the more exoplanet proposals you put in, the more time we might get. And so with that, I just wanted to say, not just thank you to everybody who made the telescope what it is today, you know, that we could be standing here having a whole symposium on this observatory and the science, but thank you to everybody using the telescope too. I definitely didn't capture all the results in this talk that I wanted to, but this is a laundry list, my last slide here of take home points, a laundry list of things I touched on of, you know, different challenges and insights we're having, but challenges in a good way, challenges mostly in rocky planets, I will say, again, mostly because of star and because rocky planets have thin atmospheres, but it's giving us challenges to be creative in our observation strategies and modeling and everything. But I think, you know, challenges can be fun. And so I look forward to, you know, the next few years of science as we move on. But I think I'll leave it there because I'm at the yellow light. Thank you.
Thank you for a magnificent talk. I think we have time for some questions. You have an online question?
Yes, we got one online. So from Natalie, she said, I would love to know if the instrument teams have any new knowledge of the noise floor attainable in the time series mode, especially when observing a very bright hot planet, hot stars.
Yeah, so I didn't talk too much about systematics, instrument noise, all that. Like that is obviously a major role in what we can learn about these atmospheres. So honestly, the teams are constantly working on this. So the Space Telescope Science Institute actually brought on a bunch of new exoplanet people to help also work on this, work on these instruments. And so I think it'll be coming soon. I know there's papers coming out all the time. I can barely keep up. But I think we're also going to hear more about this. Like I think Tom Green might be touching on some of this in his talk after me. So that's a pretty vague answer, but I think, you know, people are working on it.
We got another question from Elizabeth Tasker from Zoom. He said, for the Orion Nebula planets, what's the best way to follow up this candidate? It's thick dust, so can other telescopes spot this?
Yeah, so with the Orion Nebula, so I know, so it was with NearCam, the observations. And so I think, I don't know how many, you know, filters they used exactly, but I suspect, you know, different wavelengths would help get us, you know, the measurements you need. So establishing the colors of the objects, right? And making sure that they really are planetary mass, and as well as more modeling. So yeah, I think people are working on this too.
Yeah, thank you. This was a specific question. I don't know if you can answer it, but I saw your diagram about TRAPPIST planets, and I have a project I think to submit a proposal for to observe TRAPPIST-1, 1b, which has been, according to the brightness analysis, they say it probably does not have an atmosphere. And I wanted to see, to confirm or disconfirm it with James Webb. So you think this is within the capabilities of James Webb to discover an transmission spectrum for TRAPPIST-1b?
I mean, you could consider that. So the program I mentioned with TRAPPIST-1b and E combined, right? So they are getting 15 transits of TRAPPIST-1b as part of that program. So you could consider, you know, leveraging that if you do want to put in a proposal for something either to add on to increase the signal to noise. But yeah, I think you'd want to use, you know, the exposure time calculator and do all that to see, okay, what might you actually detect? But it would be a challenge, you know, especially with scheduling. That's the problem with some of these targets is TRAPPIST-1's on the ecliptic, which has low visibility also. But if you know, design the program and the TAC approves it, you never know.
Yeah. So my colleague says that maybe you should make multiple targets and then as part of a program.
Yeah.
Thank you.
You're welcome. Okay.
Yeah. Thank you. I have a question about the direct imaging of the white dwarf modally. And so do you consider this already confirmed before you have a second epoch?
No, these are definitely candidates. Yeah. And so I think they actually, yeah, I don't know how many epochs they got, but they were obviously close in time if they did get any. So I don't know if they're getting more. I would assume so, but that would be obviously a good way to.
Right,
to
the
track
only
this.
way.
Yeah, yeah. All right. Thank you.
A brief factor to interrupt. Is Jean-Michel in the room? I can't see him. Oh, okay, good. Our next speaker is Thomas Green. He's going to tell us about the JWST Manatee Project, atmospheric composition clouds, chemistry and processes, wow, of a diverse exoplanet sample.
Thank you, Andrew. And I'd also like to thank the organizers for accepting this talk and thank Nicole for giving such a great overview of the big advance that James Webb has already made with characterizing exoplanets. So this is going to focus on the atmospheres of exoplanets with this guaranteed time program. We started putting this together in 2016. There are a lot of outstanding questions about exoplanets that I'm sure you all are thinking as well. Why are so many of the exoplanets that we know of unlike anything in our solar system? There's so many bigger than Earth, smaller than Neptune and Uranus. What are the chemical compositions and temperature profiles of these planets and circulations? And how do they compare to their parent stars? Why are some atmospheres not in equilibrium? We know that some planets are very cloudy or hazy, like GJ 1214. And why are some clear? What are the temperatures, the day and night sides of planets? How does the energy circulate between the day and the night side? And how are these exoplanets similar to in terms of composition and also influenced by their host stars? And one of these sub issues here is the potential habitability of M stars. So we have this picture of how things should work. And we know as planets go from cooler to warmer temperatures, or the cooler temperatures, the carbon should be mostly in methane, less than around 1,000 Kelvin or so. And then as you get warmer, you should start to see it's more favorable for the carbon to bond with oxygen, CO, or CO2, depending on the overall metallicity, and then hotter planets as well. So is that reality? Here also, we have some ideas of how clouds should work. Some species will condense at warmer temperatures, these metals and silicates, and then drop at cooler temperatures, and we start to have hazes at cold temperatures because then the methane gets photodissociated. So is that the reality? We put together this Manatee program, and it's a bit of a tortured acronym. So we have MIRI and NIRCam assay for transmission and emission of exoplanets. So why MIRI and NIRCam? I'm on the guaranteed time programs. These are guaranteed time programs. I'm a co-investigator on both of those instruments. And that is our logo. And yes, there are stickers. If you want one, I have some. So the strategy to address those questions is to, we put together a diverse sample of 9 planets. I'll show you that in a minute. Look at a large range of wavelengths. That was pretty much key to probe the composition and temperature. Sometimes we have multiple features of the same molecules. And that has been important. Then also observe both in transmission and emission, so we can probe different parts of the atmospheres. And then compare the compositions with the host stars to understand formation. This is shows that the absorptions of some common molecules from this very nice review in 2019 by Niku Marudu-san. And this shows that Hubble over here, between 1 to 2 microns, wide field 3, did most of the characterization, mostly saw water, was the blue molecule there. And with this program, we're mostly focusing between here and here. There are many more species. There's a CO, CO2, methane here. and we can add the Hubble data to get better constraints on water as well. These are the planets we observed. So going from a hot Jupiter all the way down to an Earth mass planet, and also going from warm, hot temperatures to most of these are below 1,000 Kelvin, where we should start to see these both competition between formation of methane and the carbon monoxide, carbon dioxide. A number of these you see are pretty low mass. So these are Neptunes and these mini Neptune planets here. This is our team, and I won't go into all the names, but we have experts in the planning and the instrumentation. Getting one key thing is going from the observations to getting an astrophysically correct spectrum. That was JWST does not have as many systematics as things like Hubble, because it's a very stable environment, but it still took a lot of work. And we have our retrieval and modeling team is mostly based at Arizona State University in the United States. And we would go through successive feedback. We'd have 3 people reduce the data. The data would all look alike from these 3 independent reductions to the eye, but they would be different in the retrieval. So then our retrieval experts like Louise Wilbanks would throw it back to us. And then we realized some things. And if we get to the time, I can show you how we dealt with that. And then we could get an idea of what is the composition of these atmospheres, temperature pressure profiles, but it sometimes would not make sense because of things would be out of equilibrium. Whoops, wrong button. And so we'd have to have theorists involved to do the interpretations. And that has worked pretty well. Here are our initial results. So no atmosphere on TRAPPIST-1b. This was a MIRI thermal emission. This has been very conclusive. We have since, with the European group, done a phase curve observation. Hopefully that paper will come out soon. We have the best measurement of methane in an exoplanet, both transmission and emission. We are constraining compositions, including C to O and photochemistry of Neptune and mini Neptune planets, these here. Nicole showed an example of WASP 107. 3470 is a really nice mini Neptune. And 1214 we're about to submit. We do have features in this planet. And also we use thermal emission to constrain composition clouds. I'll show you an example of that. We've got one paper out, another one in the works. So the best measurement of methane in exoplanet was this Bell paper in Nature last year. This is both transmission and emission on this hot or warm Saturn planet. This is WASP 80b. So the black lines are the data, and and the blue is the overall model. If you leave out methane, you get the orange. So here in the transmission spectrum, you see that it's quite significant. It's about a 5 sigma detection. And so if there were no methane, the data should follow along the orange lines. Likewise, there are no water. The data should follow along the green lines. And here, the same thing in emission. The 2 abundances are consistent. And we find there's about 10 times less methane that you would expect from chemical equilibrium. So this has been a common thing in planets, and I'll get into why in the next slide. And this was done by Taylor Bell. This was a spectrum of WASP 107. It's a recent paper, I think it was on the cover of Nature in June 28th or so. Nicole showed it. This is like a little blow up of one region, but we put together data all the way from less than a micron from HST with wide field 3, the shorter wavelength infrared GRISM, all the way going out through NIRCam and then MIRI data. So MIRI were published separately and first with our European collaborators, but we had to put it all together to really find out what's going on in this planet. We found out, so there are how many molecules here? We have 1, 2, 3, 4, 5, 6 molecules. And as Nicole showed earlier, it also includes photochemistry and SO2. And the methane is detected, but it's really underabundant. It's 1,000 times less than what you'd expect at this temperature. And this is also a very low density planet. It's only 1.8 times the mass of Neptune, but the radius is the size of Jupiter. So why? all of this. So we get a metallicity of about 10 to 20 solar, which is about what you'd expect from the mass. C to O is subsolar, so it looks like there's more oxygen, so more accretion of ices, as Nicole showed. And what we think is happening here is that there's some internal heating due to eccentricity. It has a measured eccentricity. A lot of these small Neptunes do, and that there's some vertical mixing. So the closer to the core is hotter, and that's getting mixed up to the surface. This is the limb asymmetry of this planet. Nicole showed limb asymmetry in WAS39. It was about a 1 or 2 sigma effect. This is more than a 3 sigma effect at these wavelengths. So this is just one short region. This has been accepted by Nature Astronomy. And the black lines show the models in terms of clouds and a temperature difference. Looks like it's about 180 Kelvin temperature difference. It's even more surprising that we have limb asymmetry in a planet this cool. It's only about 700 Kelvin equilibrium temperature. But here you see this is the evening. This color is the evening, and it's just much higher. So and that's because it's hotter and less cloudy. So both clouds and cooler temperatures, and this is in the water band there. So it's very sensitive in the water band. These data have been extended actually with MIRI and also with other wavelengths with longer near-cam wavelengths, and it holds up. And we've got a consistent picture with that as well. And that was by Matthew Murphy, a student at University of Arizona. So this is by Thomas Beatty. This is, I think, perhaps the best example of composition of a sub-Neptune, GJ3470b. These are the data reduced by 3 different pipelines. And they look the same, and they also retrieve the same. That's the key thing. And this shows the atmospheric compositions that go into that. So water, methane, SO2, CO2, a little bit of CO. So most of the carbon here is in CO2. And that is because the metallicity is very high. It's about 125 times solar. And it makes sense because Neptune and Uranus in our solar system are about 100 times the solar metallicity as well. So as you go to these smaller mass planets, it looks like they have higher metallicity atmospheres. And CO, like some of the previous results, are subsolar. It looks like there's, again, perhaps more accretion of ices. This is the lowest temperature planet with this SO2 photochemistry. Also, again, that bump is there. This is an emission spectrum. And it's a panchromatic emission spectrum of this the Saturn mass planet, WAS69. It's a little under 1,000 degrees. And so these points are the data. So what's interesting here, and then this is the planet flux divided by the star flux. You see this big CO2 absorption. So the other thing that you see here is that it's compared to a single temperature black body, it's bright at short wavelengths and it's faint at long wavelengths. So that was sort of puzzling. So what's going on? So it's almost like it's too hot down here and too cold down there. We're able to figure this out by putting together some models. The best model to fit it was a cloud model, so that the clouds have producing some albedo. The short wavelengths are causing some reflection of the light, making the light brighter here. And then there's causing also some cooling over here at the longer wavelengths. And so it gets the overall spectrum to be consistent. We have some good candidates for composition, some of the clouds. But it looks like they don't fit quite well. That has been a problem. Also, we see that the clouds are patchy. We've done eclipse mapping of this object. I don't have the time to show that, but it's in this paper that was recently published in so about 2 weeks ago in the AJ. And so you can actually see that the clouds are around the terminator, around the edge, and the day side is, and like the substellar point is very warm. So we can, from watching the map of the eclipse and the planet go behind the star, we can figure that out. TRAPPIST. Okay, so as Nicole showed, TRAPPIST-1c by the Max Planck group. These are both observed with MIRI in thermal observations. And I see I'm about out of time, so there is no thick atmospheres in either one of those. I promise I'd give some science lessons, but perhaps I should take them as questions. and also some lessons about the data analysis as well. So thank you, and I'm happy to take any questions.
Yeah, Jeffrey Linsky, University of Colorado. I'm wondering, you showed an example of extremely low methane abundance in one of the planets. And I'm wondering whether that's Lyman alpha photodissociation of methane in an atmosphere where, as you say, there's a large vertical mixing. Could that explain the very low methane abundance?
I don't know if our group hasn't really looked into the UV of that planet, which is WASP 107. It's about a K7 star. We have looked into WASP 80, another one that the UV. So I guess that I don't know about what has.
The reason I asked the question is that there's a very good overlap, spectral overlap between Lyman alpha and methane photoabsorption bands.
Okay, so let's talk about that later.
Thank you for your talk. Would you please tell us your top science lessons?
Okay, thank you for the setup. So some of the science lessons is that we need panchromatic spectra to understand really what's going on, but they can be difficult to interpret. We can get different results. Sometimes like a segment of the wavelength will be published. They'll find, some particular types of clouds, but we find when we do all the spectrum, the clouds are more complex. Also, you need multiple features of the molecules. These low abundances can be understood usually in terms of this vertical mixing, this low abundances of methane. It looks like we have this high KZZ parameter that's causing warmer material to get up towards the photosphere that could be probed in transmission or emission. Clouds and hazes are ubiquitous, and they can be inhomogeneous, which you've actually seen in some of this emission stuff. And sometimes we have good candidates for the composition. Sometimes we do not. And we can also get information about the interiors, like this one with a really low methane abundance seems to be consistent with what's going on in the eccentric heating. There's a correlation between lower masses, higher metallicities, and terrestrial planets interior to the habitable zones of M stars are not good places for atmospheres.
So our next speaker is Zuhair Ben Khaldoun. He's going to tell us about TRAPPIST North. It's a Bukamdan observatory, a success story in the field of planetary sciences.
Thank you, Andy, and thank you all for coming. In the three last talk, as you see, you noticed they speak about TRAPPIST system, and it's good to present here the TRAPPIST telescopes. As you may know, we have one of the TRAPPIST telescope at the Oakhamden Observatory. I already speak a lot about Oakhamden Observatory in Focus Meeting 1 and yesterday in the Division C. Just show you this slide where show the location of the TRAPPIST among other dome we have at the observatory. So the TRAPPIST telescope, as you know, TRAPPIST North as well as TRAPPIST South is the twin telescope, one in northern atmosphere in Oakhamden in Morocco and the other in Chile in southern yes. And the model is Astelco Ricci Christian. The diameter is 16 centimeter. And the dome, it's a Gombado model with 4 6.2 meters of diameter, and they use Totec automatization. And now the TRAPPIST-NOR is dedicated 15% to exoplanet and 50% to comets. The telescope is equipped with CCD camera, on-door model, and the pixel size is 13.5 micron, and the pixel scale is 0.6 arc pixel. We also have a filter well, excuse me, with the both side equipped with the exoplanet filter, FW1, and for comet, we use the other side, FW2 comet. Yes, we monitor the observation. I will present here how we monitor this telescope. Of course, we have a weather station to check the condition, the meteorological condition, and also all sky camera to check the sky. And as you can see here, we produce some weather graph. Also, we use other facility we have in the site, especially from MOST telescope to help to check this condition. We developed an interface for making the observation easy for users, and dependent of the weather condition, we have the safe mode. When we have the safe mode, we can start the observation. To monitor to the telescope, we have several possibility. We mainly use what we name automatic control program as ICP. This is a software for indeed this is an interface to use the telescope, and of course we can also use directly MaximDL to use the telescope. You can see here an example of both interface of MaximDL and the ECP software. We use a script for each target we would like to observe, and you can see here an example for WASP 161, where we have the time of starting observation and the display image during observation, autofocalization, number, maximum of image. Also, we have to set the binding of CCD, to choose the filter, and of course to set the exposure time in second, and the name of the target and the coordinates, and of course the time to end the observation. And both we can use directly MaximDL for that. Here is the example of CCD image we obtained for both comet and exoplanet. We need to prepare observation, of course, and to choose the filter depending of the star. We have to observe the nature of the star. We can use several filters. We also, the most important parameter to set is, of course, the exposure time, and which depend of magnitude of the star, and also of the seeing condition. So we develop a short program to set exposure time, depending of the condition I have underlined, but also depending of the capacity of the telescope and the sensitivity of the camera. Yes, we start the observation when the sky is clear, the wind is less than 30 kilometers per hour, and the humidity less than 16%. And target elevation must to be up to 21 degree. To start the observation, we need the time of starting, and we use, of course, ephemeris of transit for that. Yes, this is how to choose the filter for cometary program, and you can see, you can refer to Farman and all 2004 explain why we proceed. After that, we have data, and we proceed to reduction of transit data. First, we use IRF and Trafot, which is developed by Michael Gillon from and Bordanov from Belgium, from Liège University. This is the classical, of course, classical photometry aperture to infer the light curve of our observation. This is an example of light curve we obtain with the telescope using IRF and Trafot. We analyze this data, and we can infer the parameter of the planets using Markov chain Monte Carlo, also developed by Gillon, and you can read more about that the publication of Michael at 2012. Yes, this is a classical way of using this model, but as I said, you can refer to this publication for more detail. So we obtained the light curves and also the model. Here is the example of Trace 3B made by Khalid Barkawi, one of our PhD students in this field. This observation is published in a Journal of Physics in 2017. Yes. Now, how we can choose data to observe the target. Mainly, we use now as several other group the test candidates. This test, you know, yes, this is a transit in exoplanet survey satellite. More than 700 exoplanet candidates detected up to now. Among this, we have more than 400 exoplanets already confirmed, and many of false positive, and more than 500 exoplanet candidates need to be confirmed so far. We contribute to the test candidate confirmation with how we made the selection of target. The selection of test objects of interest is based on the test transit finder, TTF. TTF is lists all the observation candidates from a given geographic site and a given night, and provides all the needed information. like equatorial coordinate, magnitude star, etc. And test of interest lists are periodically for the TRAPPIST, of course, from 1 to in general from 1 to 5, and for the TRAPPIST we prioritize from 1 to 3, which are generally small planets with a radius smaller than Neptune, less than 4 radii Earth. The community of the test community use now Astro Image program to do all the program of observation and analysis, as you know. So we switch to this software for doing the analysis. This is the example I get from Morad Ghashwi, who is one another student, PhD student. We will defend his thesis in October, in next October, Marrakesh. This is an example of one of the test of interest target. And now I will present some statistics of the TRAPPIST. We have 285 observation for TRAPPIST North and 369 for TRAPPIST South. And you can see here the confirmed planet and validates planet and the eclipse in binary, blended equivalent, nearby equivalent, and so on. And as you see, we have in our program to verify the planet candidate levels. This is for a cometary. You can see here all the comets observed with the TRAPPIST North up to now, since its commissioning in 2016 until now. The graph covers more than 100 comets, excluding those for which we only conduct the observation on a single night. The number at the top of the bar represents the number of images taken for each comet. And you can see that for some of this comet, we go more than 1,000 of observation night. I present also as an example the statistics we have for the TRAPPIST North for 2023, which was not a good condition, meteorological condition this year, but more than 50% of the time we can observe. This is the number of publications we have on TRAPPIST North. And as you can see, we have 7 papers published in Nature. Yes, not have. You can switch to conclusion. TRAPPIST North is a symbol of international collaboration. It has made a significant contribution to planetary science and astronomy. From the TRAPPIST-1 system to insight on comets and asteroids, it has expanded our understanding of the solar system and beyond. And the TRAPPIST North fostered technological progress and aspired the next generation of Moroccan astronomers. And we can also say that the success of TRAPPIST North has greatly contributed to the development of the Camden Observatory, highlighting the site's excellent astroclimatic condition and strong local logistical support. Sorry for praising the time. Yes, thank you.
There's been a small change to the program, so our next speaker will be Jean-Michel Desert, who's going to tell us about observations of V1298 Tau B with JWST. Thank you, Mr. Jean-Michel.
How much time do I have? How much time? Okay. All right. Good morning, everybody. Let's see, this is a change of program. Thank you to for the organizers to giving me the opportunity to give this talk. This is a talk that was not planned in the schedule, so I think the previous speaker was not available, so I'm going to fill in. This is a talk that I'm giving on behalf of my PhD student, Sogata Bharat. So all the work that I'm presenting here is really his work. Is currently writing frenetically his thesis, PhD thesis, in the Northern Hemisphere in Europe, in Amsterdam. I know that there is a heat wave there, so he's working very hard. But what I'm going to talk today is about young transiting planets. So in the past decades, thanks to the mission like K2 and TESS, there's been a fantastic work done on finding transiting planets around young stars. Typically, the planets that were found around those young stars were detected by direct imaging. You have, for example, Beta Pictoris or HR 8799. They are less than 20 million years old. And typically, that's where we find those planets. But now we can find transiting planets around 20 million years old stars. And therefore, we can study them by using the technique on transmission spectroscopy, emission spectroscopy that you've been hearing this morning so far, applied to those planets. And I'm going to talk about a very interesting system, V1290 that I will introduce you to. So I'm going to talk a little bit about the first transmission spectrum on those planets. We didn't have transmission spectrum on young planet before. So I'm going to show you those first transmission spectra. And I'm going to show you JWST spectra for this also. And I'm going to talk about some challenges that we have in characterizing the atmosphere of those planets. And I can tell you already that the stars, the young stars, pre-teenager stars are actually temperamental. They are quite difficult to characterize. They are very active, variable. And so this is the main challenge already that we have. But the key opportunity here that we have is that we can study the early evolutionary mechanism of those planets. What we want to see is how the planet, for example, in the solar system, evolved when they were very young, when they were 20 million years old. And there we have the opportunity to do that. So many things are happening in the first 20 million years that will be crucial for the evolutionary of the system that we are looking at. So really understanding what's happening there is key. So let me introduce you a little bit on the V1290 system. This is a system that was detected first by K2 transiting system. There are 4 transiting planets. They have between 5 to 10 times the mass, the radius of the Earth. And they're, interestingly, it's a compact system, really in mean motion resonance, 1 to 2 to 3. Planet B orbits at 24 days period, right? And D at 12 days period. So this is a planet that we are going to look at, C and B. Specifically, when you look at them in the radius period diagram, and where you see the radius valley of those planets, you see first you have the Jupiter-type planet and the Neptune-type planet, and you see already how planet TOB is an outlier. It's an outlier already by its age, but it's an outlier just from its size. This is a planet that will evolve, and we know that this planet will contract, but also may lose part of its atmosphere through atmospheric escape due to the UV radiation of the star, X-UV radiation of the stars, but also because right now the planet is young, there are core-powered evaporations. I'm going to come back to that, but the internal temperature of the planet blasts off the atmosphere. But this is still a planet that is contracting as we speak. So what we're trying to understand here is interesting on multiple levels. We're trying to look at the young planets, how they evolve, the late formation, the early evolutions, but also we're looking at a multiple system planet. So we can compare different planets within one multiple system. And this is also something very new here, that we can really look at the early evolution for multiple planets. And I don't think actually we've been observing actually multiple system planet for mature planets. So this is also something, a new development that we're trying to do in my group. This is a beautiful spectrum from the Hubble Space Telescope. So pre-JWST, we are between 1.1 and 1.7 microns. And what you can see here is a strong detection at 400 per million of water. When you compare it to other spectra with HST from other planets, this is really large. This is a large signal-to-noise ratio that we're observing. So we see a clear atmosphere and a primordial atmosphere, very low metallicity. For a planet of the size of 10 times the radius of the Earth, this is rather expected. However, the planet was initially thought to have the mass of Saturn from radial velocity, while it has about the size of Jupiter's. And that's really interesting because when we looked really at a model of a Saturn hydrogen-rich model, you see that the model will bring you about to this level for that metallicity, solar metallicity. And we really rule out 100 times 100 solar mass here. And when we fit the mass of the planet just from the scale height, so we have the surface gravity, we have the temperature over surface gravity when we are looking at the scale height. And just from the surface gravity, we bring down to an upper limit at 3 sigma level of about 24 solar mass. So we don't see a Saturn mass planet, but actually a Neptune, super Neptune mass planet. So that's very interesting because we're changing really the regime. We have also an improvement of 1 order of magnitude on the precision on the mass determination by measuring by the scale height, the mass of this planet. So this is really something that moving forward, it's very promising. When we're looking at young transiting planets with radial velocity, we have a lot of struggles to measure their mass. Now we may have an avenue when we have a clear atmosphere, like in this case. But we rule out a metal-rich atmosphere, and we have a mass comparable to Neptune, more or less. And interestingly, we do not detect the methane. Why is it interesting? Because the equilibrium temperature of this planet, about 700 Kelvin, 670 Kelvin, at this temperature, chemical equilibrium is telling you that you should have methane, and we don't. So we already know from the spectrum, from the HST spectrum, that we are not at chemical equilibrium, and we are trying to understand why this methane disappeared. And one of the direct culprits for this is that there is a high internal temperature. This is not totally unexpected, given that this is a young 20 million years old planet. High internal temperature means that the planet is still contracting. And we expect to, we find that the temperature is about 500 Kelvin. This is still higher than what we would expect for this planet at this age. What we've done is go further, is that we have those multiple planets in the system, so we can compare the spectra of those planets. And that's becoming very interesting because we don't find the same spectra for planets that have roughly the same mass. So there are two scenarios. Either the densities of those planets are different, could be, so slightly different metallicities maybe, or because there is a UV flux, strong UV flux, and a relatively large distance between those two planets. Maybe haze is formed on the first planet because the UV, because of the UV, there could be a difference of composition between those two planets. So that's two possibilities, two scenarios for those planets. But moving forward, I think we will see more and more, and I hope we will see more and more comparison of transiting planets within the same system, because it tells us a lot about the formation of individual systems. But this is a HST spectrum, that is a JWST spectrum that we obtain. Remarkably, this is not a fit of the HST observation that I just showed you. This is actually an overplot of the model fitted to the JWST data. So we have an excellent match between HST and JWST. So we are, what we find is that we see the strong CO2 line that Nicole showed in the first JWST spectra. We found SO2 that we think is due to photochemistry. So second things telling us that we are not at chemical equilibrium. We have photochemistry going on and lack of methane. There should be a strong methane line at this equilibrium temperature that we do not see. So we confirm the lack of methane that we saw with HST, with JWST. We measure the metallicity, carbon C2O ratio, and so forth. And we also look at different haze scenario, whether we could feed the data with different haze. This is the methane, that's where we would expect the methane at the equilibrium temperature, chemical equilibrium. But obviously, we are far from this in the overall spectrum. We refined the measurements, the mass measurement of the planet. And now we are no longer at 24, like a super Neptune, but we are now at 12 Earth's mass. So we're really going down now in mass. So we have lost 1 order of magnitude in terms of mass between the radial velocity and the JWST spectrum. This is really interesting because now we're in front of a planet which is a precursor of sub-Neptune super-Earth, the planet that we see massively in the demographic of planet. We see here baby super-Earth that is going to lose its atmosphere and that is currently losing its atmosphere. Although we don't have observational evidence that the planet is losing its atmosphere, we think it does from the UV flux of the stars and from the internal temperature of the planet. Indeed, we look at the evolutionary internal temperature of this planet. What we find as function of the age is that V1298b has a really high temperature, 500 Kelvin internal temperature, compared to what would be expected for this age of this planet. Now, there are several hypotheses here. Could be that we are just looking at V1298b and it's just formed. So the age of the stars is actually misleading us on the formation of the planet. Could be perhaps extreme given that it's 20 million years old. So that's a big difference, but maybe we can gain 10 million years old. The second thing is that there could be processes that increase the temperature, the internal temperature of the planet, like collisions with leftover debris in the disk. Although we don't see a debris disk and they are very weak lithium line on the star, so we don't see really evidence for accretion. We have maybe tidal effects that are going on. The planet may experience tidal effect on eccentricity damping and tidal locking, which will really significantly increase the temperature, particularly depending on the inclination of this planet. So we realized that we can reach really the temperature that is necessary from tidal locking. There could be ongoing dynamical instability, like planet-planet interactions that increase internal temperature of the planet. Those planets are in mid-motion resonance in a compact system. Certainly, the energy alone cannot explain the high temperature of this planet. So there is still more to learn about this. But we really see this planet in the earlier phase here. I'm going to, I see our chair, the interesting things here that we can really compare for a similar mass, this young planet to more mature planet at 500 million years old. Remind you, it's 20 million years old. We are 500 million years old. And also more advanced, like GG1214b, more mature planet. And we can now compare those different planets, not only between the same planet in the same system, but between young and mature planet. And I'm going to leave you with my conclusion. So I presented you the first transmission spectra of young transiting planet. They may have thought to be more Jovian type planet, but we think they're Jovian sized with some Neptune mass. So I gave you some first glimpse at the evolution of this. I want to also emphasize the large program on the cycle 3 JWST, the Chronos program led by Adina Feinstein and Louis Wellbanks. And it's a really very interesting program where they will now survey all those young transiting planets to do what I've just showed you for this first one, B1290 Ecto B. Now really do comparative exoplanetology of young transiting planets. Thank you.
Yeah, thank you. It's Bill Wells from San Diego State. Thanks for that great talk. Maybe I didn't quite understand, so maybe you could explain, help me understand. I think you mentioned a very big disparity between the mass based on the spectroscopy and the RVs. And what is the origin of that discrepancy?
So there is a great paper written by Sarah Blunt about this. The key issues is that the stellar activity, this is a star which is highly active, chromospheric activities, and that affect the measurement, the radial velocity measurement. So the precision that they reach in the end, in the determination of the mass is plus or minus 50 Earth mass. And we go down to a precision to plus or minus 5 Earth mass just by the transmission spectrum. We are not always in a situation like that. Obviously, precision, radial velocity really are superior in mass determination when we are looking at hot Jupiters or any other planet. But in this special case, because the radial velocity are so difficult to determine, now there might be some promising studies made with decorrelation with the activities and so forth. But so far, all those studies for this system have not been successful. It's really highly variable. So
Are there any TTV mass estimates?
absolutely. This is a great thing about this system. There are TTVs that were not discovered initially, but have been subsequently discovered. A plus or minus 2 hours on the TTV effect that, so we see an anti correlation between these two either planets D and C, which allows to measure their mass, and their mass are actually found to be really low, lower than 10 Earth mass from the TTVs. So, and that's consistent with what we find with the transmission spectrum. So all those masses now are much lower than we thought. So this is really a compact sub-Neptune system and no longer giant as we thought initially. Thank you.
Our last speaker of this section is Edward Gomez, who's going to tell us about exoplanets in education, the rise of robotic telescopes. Sounds scary.
Thank you. And I'm glad that some of you have stayed for this, even though we're running a bit late. Yes, I work for Las Cumbres Observatory, and we have 25 telescopes situated at 7 professional observatory sites around the world. The 10 highlighted telescopes there formed our 40-centimeter network. That's also our education network. And as the education director, I was tasked with forming an education program to make use out of these telescopes. And that's quite a daunting task. There's quite a lot of time available on those telescopes, and I wanted to make the best use out of that time. A little bit more about our network, if you've not heard of it. We have 2-meter telescopes, which have imaging and spectroscopy, 13 1-meter telescopes, which also have imaging and spectroscopy. But the ones for education are these 40-centimeter telescopes here. They're used by scientists as well, but we try to limit that. So this is a close-up on our 40 centimeters. They're plane wave delta rho telescopes with CMOS cameras. Actually, they were Meads with SBIG cameras, but we've recently had some funding to replace all of those. These are brand new telescopes. But we built the mounts ourselves, and they've been extremely endurable mounts that are left exposed to the elements. So we have a lot of telescopes. What do we do with all of that time? You'd think, well, you create an education program that's internal to your institute, you know, you find individuals to work with, but with such a lot of telescopes, it became very obvious that that was an unsustainable and not scalable at all. So in 2017, I came up with the idea of the Global Sky Partners. So instead of having an in-house project, we invited people who had ideas, were already running astronomy education projects with robotic telescopes, some of them not with robotic telescopes, to use our telescopes and to do educational work. Some of these people had a really strong track record, people like Hands on Universe and GTTP. Other people just had an idea that they wanted to do something with exoplanets, say, and they had a target audience, say, high school kids, and they needed a robotic telescope to do that. Because we've got this robotic telescope network, and it's operated largely as a single instrument in the different classes. You don't target a particular telescope. You say, I want the 40-centimeter telescopes to take observations of this phenomenon or this target within these constraints. So we're ideally suited for time domain astronomy. So exoplanets is a natural partner there. So to become a global sky partner, we have an annual call for proposals. We've realized that if we let this open to anybody, we get cheeky scientists trying to sneak science projects in by the back door. No, that's not allowed. We'd also, if educational projects, you'd get a lot of Western European, US, North American universities trying to do Astro 101 labs. Nope, that's going to use up all the time as well. And to have the maximum impact for this program and for this resource, we target underserved and underrepresented communities. Not all of our projects target those communities, but a lot of them do. And because we've got such innovative telescopes, we'd like the projects to be innovative in some way. But they fundamentally have to be educational. To use these telescopes as under the Global Sky Partner Program is absolutely free to the end user. There is no charge to them. That goes right back to the fact that we want to engage with the people who wouldn't normally have these type of opportunities. During the last 12 months, we've been running with 41 partners. Some are as small as a single class, who actually are doing amazing things, and some are as large as 1,000 teachers in Brazil at every Brazilian state, including the administrative district. They do a variety of different projects. These are actually some teachers and some groups from our Brazilian partner. And they do everything from hunting asteroids, just the very first 3-color images, to competing in the International Olympiad. The partners' topics cover, roughly speaking, these 5 different areas: citizen science, teacher training, student research, by which I mean the students do a research project and very often they follow it through to writing a publication. Observing campaigns, where normally scientists say, we want some data, can you please take the data, and then we'll involve you in the process of analyzing that. And some artistic and inclusive outreach projects. And some of these have been tactile astronomy, so taking images and then 3D printing them. Some of them have been sonification projects, but they've always been quite innovative. Now, exoplanet projects touch many of these different areas: citizen science, observing campaigns, teacher training, and student research. Unfortunately, we have, and fortunately, not unfortunately, and fortunately, we have 2 partners which are specialists in exoplanets, Exoplanet Watch and Exoclock. Has anyone in the room heard of these projects? A few, yeah. So they mostly do the same thing, but for different purposes. Exoclock is a European project that works with the Ariel mission, and Exoplanet Watch works with JWST. The idea behind these 2 is to save these space missions time by having accurate ephemeris for exoplanet transits. And so how they do that is they ask their their participants if they can take very accurate, or not necessarily very accurate, but just a few measurements of the transits of poorly studied exoplanets, so that there's a good database of well-known and well-timed transits. Now, then you do get some TTV events, you do get some transit timing variation there, which is always a nice bit of science. But really what they're looking for is not discovery of exoplanets, but to really have a tight constraint on the ingress and egress and the midpoint of the transits, so that then any people that want to observe using JWST or aerial don't have to have such a large window. They have a really good idea of how long that transit's going to last. So what we do is we provide these groups, we provide them with 50 hours, particularly for education, for teachers to use their tools. And each one of them has developed some really, really excellent analysis tools. Exoplanet Watch's analysis tool's called Exotic, and it's a Python-based tool that you can run on your computer, but you can run it in a Jupyter Notebook or a Google Colab. ExoClock has developed a piece of software called HOPS, which again is Python-based, but is more of a graphical user interface. They both run teacher training, and they both have extra educational resources about exoplanets. And the benefit of being involved with this program is that the school teachers and the students can contribute to science. These are two examples of the output of firstly Exotic and then HOPS on the other side. This was actually sent to me by a school teacher using LCO data, using LCO time with her students 2 days ago. And the one on the far side is actually some data I took just for illustrative purposes. And you can see there that the software has picked out the predicted start and predicted end times then, and fitted the transit curve for them. So they take the data and then they upload this into either the ExoClock database, or Exoplanet Watch uses the has a deal with IAU, and they use their database to store all of this data. But not only do they have their own projects, but they support other global sky partners who want to have exoplanets as part of their suite of things that they offer their audiences. Some of the partners are geographically located with their audience, and some run online projects. There's a huge diversity of different partners. One such partner is Boyce Astro, which is based in San Diego. And here are two of the students presenting their exoplanet research at a conference of professional scientists. So these are two high school students. Can any of you imagine going to a professional astronomers conference and presenting work that you've done with your teacher? It blows my mind that they not only have the confidence in themselves, but they have confidence in what they've done to do that. And another one of our partners that partners with Exoplanet Watch is Stanford Online High School. That's their teacher there. And they regularly submit their transit data to the Exoplanet Watch project. But they also were involved in the Naming ExoWorlds project as well. There, and those are all her students for the Astrobiology Club. So the achievements as the program of a whole. We've engaged through the Global Sky Partners nearly 60,000 people in the last year. So that's teachers who are direct audience plus their students, which is an indirect audience. We've had an impact in 41 countries in languages that I don't speak. So if I kept it in-house, I never would have been able to have addressed and had any impact on those audiences. We've submitted, or I should say, not we, the students have submitted over 30 complete and partial transits into the AAVSO and the ExoClock databases, which have provided extremely useful measurements. I don't have it on the slide because I only heard it a few hours ago, but the PI of the Exoplanet Watch project, Rob Zellum, has told me that has saved 4 hours worth of JWST time. Doesn't sound like very much, but that's several $1 million worth of observing time it saved. And they've published 24 papers in peer-reviewed journals. That's high school students, not all of those on exoplanets, actually, most of them on double stars. And since the program started, there's been 130 papers published in peer-reviewed journals by high school students. So if you want to find out more about all of the work that the partners are doing, you can have a look at that website there. But thank you for listening.
Hey,
Yusuf, nice to see you again.
Nice to see you.
So just before he asks his question, Yusuf is one of the people who was involved in the Global Sky Partners.
Yeah, thank you very much. And I like when you show that map, when you have all these countries benefit from this program, which is very amazing. I also benefit from it, and also my country. But I see in the map that there's a very large gap in Africa. And I'm trying to implement a project called Astrolab, so which I will be talking on Tuesday. So trying to provide, give the Africans or African students the access to the LCO. So my question is, does LCO provide trainings for teachers? I'm not talking about students, for teachers to train students.
So we do that through the partners. We have many different groups that that will provide teacher training in astronomy. But if your teachers already know astronomy and they just need training in how to use LCO, then yes, definitely we'll provide that. Yeah.
Thank you.
Yeah.
Thank our speaker again.
Yes, thank you for coming, everybody. We will start in 1 minute now. And the first speaker will be Mark Champin. And after we will have 3 other speakers, Shaima, Amri, Dominic, and Inji. So if you are ready, you can come. Yes. Thank you. So if you can put the first talk up. Great. Okay, good afternoon, everybody. So my name is Mark Clampin. I'm the Director of Astrophysics at NASA. And I'm going to be talking about the Habitable Worlds Observatory this afternoon. And I'm really talking about what NASA's doing, how we're doing the project, how you can get involved, and what our kind of timeline is as we see it right now. So this is a really nice quote that I took from the National Academy's 2020 Decadal Survey report. And this is really what's driving our approach to the Habitable Worlds Observatory. So I think this is a really nice sort of top line to what I'm going to be talking about. So let me just start off by reminding people where we are in terms of NASA's big picture approach to the search for life. And we really began that with the Kepler mission. So when Kepler flew, there were, I would say, a handful, maybe 100 or so exoplanets known, and they were primarily discovered using the radial velocity or the stellar wobble technique. And Kepler came along, surveyed a piece of the sky for 4 years, and it discovered an extremely large number of exoplanets. And as we started to develop the 2000 decadal recommendation, which was the James Webb Space Telescope, it became apparent that it would be really useful to have a mission that was looking for stars that had exoplanets, and in particular small rocky ones, that we could study with Webb. So basically, we needed a target finder for the James Webb Space Telescope. And that really kind of gave birth to the TESS mission. TESS stands for Transiting Exoplanet Survey Satellite. And as of today, TESS has 482 confirmed planets. And you can see what that means in terms of, the size of the planets on the chart. TESS also has something like 7,000 other candidate planets that are still to be followed up. And we've been following it up, first of all, with the Hubble Space Telescope. And Hubble was a real game changer here. It got the first ever atmospheric spectrum of an exoplanet. Those of you who just heard Dave Charbonneau speak at the Kavli lecture will have heard something about, how that came about with, an observation with a small telescope in a car park in Colorado. And then the very first observation with Hubble, which went from just detecting the transit, as they had done in Colorado, to actually getting a spectrum and evidence of the sodium lines. And then later on, Hubble also did the very first observation of a small rocky planet. Now we're into the era of Webb, and we're doing a lot of observations of very late type stars with exoplanets and starting to study their atmospheres and do real comparative planetology or, comparison of the atmospheres of these planets. And this is just a really nice example. This is one of James Webb's very first, very first science results. This was notable because we found evidence of sulfur dioxide, and that's, first concrete evidence of photochemistry in an exoplanet atmosphere. So Webb has continued to really, make leaps and bounds in the study of exoplanets. It's now being used to study small rocky planets and is starting to get to the point where it's actually detecting atmospheres on small rocky planets. So I think over the next couple of years, you'll see some really astounding observations coming from Webb. However, as the National Academy pointed out, we're looking at a relatively small part of the potential exoplanet zoo when we study
transiting exoplanets with James Webb. We're really looking at M-type stars or very low mass stars. Most of them have very short periods because the habitable zone and the orbits of the planets are very close in. And we cannot yet study in any great detail solar type stars, the Gs, the Ks, and so on, because even Webb cannot actually do spectroscopy of those planets due to the contrast between the size of the planet and the size of the star. So in order to do a real survey and find all the habitable planets in the nearby neighborhood, we would have to go to direct imaging. And as you all know, the great thing about transit spectroscopy is you never actually have to image the exoplanet. It's all indirect measurement. So the first thing is we have to go to direct imaging. And that means we kind of say goodbye to transit observations, and we want to get images like the one on the right, and you immediately see some of the challenge in doing this. The central star here is actually blocked out, but the bottom line is you're trying to detect small exoplanets that are about as bright as the faintest objects in the Hubble Deep Field, and you're trying to detect them at tens of milliards seconds from their parent star. If you want to detect small terrestrial planets like Earth, you need contrast levels of around 10 billion. So that really sets a very tough challenge for the next mission that we're talking about here, the Habitable Worlds Observatory. So this is what the decadal survey asked us to do. They said, start with the technology maturation and then embark on a program that will search for biosignatures from about 25 habitable zones. And they recommend that we do a survey of something like 200 to 300 nearby stars to identify those 25 candidates. They were not very specific about the size of the aperture. They suggested a 7-meter telescope if you take into account the inscribed circle, if we're talking about a segmented mirror. So they basically had told us, figure out what you need to do in order to get the candidate size of 25. So that brings us to the Habitable Worlds Observatory. So we rolled out the idea for doing this mission at the 2023 AAS meeting. And this is just a notional architecture that you see here. But the general feeling is that we should go with technologies that we've already developed. And I'll show you what I mean by that in a minute. And that we should build on the concept of using coronography. So what we're talking about is a large aperture telescope. It's going to be optical and UV. And in addition to doing the primary recommendation that the National Academies laid out, we should also have a telescope that serves as an observatory. And as you know, Hubble, Chandra, Webb have all served as observatories. Webb was really designed and conceived to find the very first galaxies in the universe, but it's also an observatory or a flagship, and it does science in a vast range of different disciplines within the capabilities that the instruments provide. And I wanted just to talk about where we are with coronagraphs for a minute. So many of the instruments on Hubble were coronagraphs. None of them were active. They were very simply occulting masks with the appropriate apodization in the pupil plane. Indeed, one of the instruments even did the occultation in the aberrated beam of Hubble and still works reasonably well. But we've reached a point where we believe we need to do a demonstration in space. So trying to jump straight to what is required in the Habitable Worlds Observatory is a bit of a leap. So several years ago, the previous associate administrator of the Science Mission Directorate at NASA came up with the idea of doing a technical demonstration on the Roman Space Telescope, which is the 2010 decadal recommendation. That's our program of record that we're completing, and we expect to fly in 2027. Roman is a survey mission. It's designed to study dark energy and dark matter, and will basically do a very deep sky survey, and it has an aperture of about 2.4 meters, which is essentially the same as Hubble. However, we have added this technical demonstration instrument to Roman, and Roman will devote a small amount of time to demonstrating the concept of an active coronagraph in space, and then we will do some science with that coronagraph as well, outside of the main survey science. So what you see here on the left is the instrument. It's an extremely complex instrument. It has 2 deformable mirrors and is doing active wavefront control of the coronagraph wavefront error. So the wavefront going into the coronagraph is measured, and then we have 2 mirrors that correct phase and amplitude, so that we have a much cleaner wavefront error going into the coronagraph. The requirement for this coronagraph is to achieve a contrast of 10 to the minus 7. And already in the thermal vacuum testing, we've been able to achieve a contrast level of 10 to the minus 8. So this instrument's going to be a test bed. It will allow us to figure out how to do coronagraphy in space with an instrument very similar to the one that we will ultimately fly on the Habitable Worlds Observatory. So on the right, you can see this animated GIF here, which is showing the sequence of how they did the high order wavefront sensing and control, and the iterations to dig what's called a deep hole around the occulting mask, which is that sort of blue region in the middle. This was done during the thermal vacuum testing, and they were able to demonstrate that they could get to 2 times 10 to the minus 8 just in the thermal vacuum testing, using those 2 deformable mirrors. So this is extremely encouraging, and we will use this as a way of understanding the requirements for our coronagraph of the Habitable Worlds Observatory. So that brings me to the big picture strategy for how we do habitable worlds. And as I said, I'm really talking here about the philosophy and how we're going to do this, rather than the exact science of what we're going to do once we built it. But we want to build this mission to a very different approach than the one we've used in the past. And the first big difference is we are going to build it on schedule. So following the James Webb Space Telescope, Congress wants us to really focus on getting a very clean cost estimate for these missions before we progress to actually building them. And one of the ways that we are going to do that is to mature the technologies first and then design the telescope. So that means we probably won't start formally designing this telescope until relatively late in the decade. And the reason is that these big flagships are extremely complex systems. And if you start trying to design them before you understand how all the technologies going into your system work together, it will end up costing way more and take much longer to build. And it's a very complex system. We see already we have active control of the coronagraph. To achieve 10 billion contrast levels, we'll also need active control of the telescope. So all of those have to work together in very complex control loops. So unless we demonstrate all this before we start designing, we're going to have problems later on. So first idea is that we mature the technologies. Once we understand what we're building, we do the design. And then once we have a very clear design with a clean cost estimate, we can proceed to building it and hopefully build it much more quickly than we have done in the past. And I'll just add that at the moment, we are finishing up the Roman Space Telescope, and Roman is actually being built on cost and schedule. So this is another sort of important milestone for our stakeholders as they look at how we're doing this project. One of the things that I've talked about a lot is maturing the technologies. So in addition to maturing the technologies before we design, we're also building on the current NASA investments we've already made. So you just saw the Roman coronagraph, that's one of them. The other one is that we built a segmented mirror telescope with a very large aperture called James Webb. So we will take the approach we've learned building the Webb as we go forward with this telescope, rather than trying to essentially retool a whole US mirror industry to build 6-meter telescopes for space. So we know how to build large segmented mirror telescopes. That's what we're going to do. The other thing that we're going to do is take advantage of what will be available in 10 to 15 years to launch these missions. So one of the other things we did on Webb was we looked at what was available when we started designing it. And throughout the program, we were struggling with mass and volume restrictions that we probably didn't need to deal with if we'd have been a bit more forward thinking. So we are looking very closely now at what will be available in the way of launches in the future. And you already know there are a number of companies launching or talking about launching very large rockets with large fairings that can take lots and lots of mass into space. And we're going to be designing to those kind of requirements. We're also going to design this mission so it can be robotically serviced at L2. So this is an L2 mission. We're going to L2 and we plan to robotically service it there so that we can upgrade the coronagraphs as we realize we need additional or new measurements. We can put new instruments in to do those measurements. And then lastly, we need robust margins. Doing coronography is very unforgiving. You just need a very small change in a requirement and you can lose a big part of your sample. So we are starting with extremely robust margins on this mission so that we don't get halfway through and realize we can now only survey 10 planets or 10 stars. So we're building it with very robust margins. This is something else that we always show, and this is how we search for life. And this is just a recognition that over the lifetime of the Earth, biosignatures that would be indicators of life have obviously evolved. So we're not just designing to be able to detect biosignatures from present day Earth. We're also mindful of what Earth may have looked like in the past, and making sure that our instrument capabilities can provide us with the required capabilities to cover a broad range of different epochs in the evolution of planets. The other thing I want to emphasize is, and I mentioned this already, but this will also be an astrophysics mission. And we anticipate that this telescope will be able to do a lot of transformative astrophysics across a broad range of disciplines, from mapping the baryon cycle in emission and absorption, doing extremely deep fields in the optical and the ultraviolet. And obviously with the resolution in the optical, we'll be able to do really amazing observations, resolving stellar populations outside the Milky Way. So this isn't just an exoplanet mission, it's an observatory for the whole community. And I wanted just to show some notional concepts for what kind of instruments we might be using. Again, we have not designed or settled on anything, but as we think about the science that we want to do, we obviously need some kind of straw man concept of what we might be doing it with. And this just gives you an example. Telescopes around 6 meters, and we're looking at a bandpass from probably about 100 nanometers to 2.5 microns. So we plan to go just a bit beyond the sort of normal cutoff telescopes when you think of thermal emission. The coronagraphs kind of speak for themselves, but we're looking at things like having a big wide field imaging camera and also ultraviolet multi-object spectrographs as 2 examples of what we might fly. One of the things that we're already taking away from this is that we are pretty much, with the kind of arrays that we'll be flying in this kind of time frame, done with bringing the data back to Earth by radio. So we will be looking at using optical communications for this mission. And I was telling someone a few days ago, when you think about the wide field camera, we just had somebody come to headquarters and pictures on an array of 8K by 8K sensors. And if you're doing time domain astronomy with those, you're going to need to get a lot of data down. So optical communications will be the norm for this mission. So I wanted to talk about where we are right now. So over the last year and a half, this program has gotten a lot of momentum. And in this year, the FY federal budget cycle, we were given what's called an earmark, which is that we were told to spend a certain amount of money on this program before the end of the fiscal year, which is September 30. We were also told to start the project office. So as of August 1st, we have created the Habitable Worlds Observatory Tech Maturation Project Office. At the bottom here, you can see the leadership. Lee Feinberg is our principal architect right now. Mike Menzel is our mission systems engineer. They both come with a lifetime of experience on James Webb. Jada Ani is our interim project scientist, together with Aki Roberge. And at JPL, Bertrand Menison and John Zima are also playing roles as they look towards how JPL will put together the coronagraph. At headquarters, we have Julie Crook as the program executive, and then Megan Anstor is our program scientist, together with her deputy, Josh Pepper. So we have a real project here at this point. So the last thing I wanted to talk about are the Habitable Worlds Observatory working groups. So at the beginning of the calendar year 24, we put together a construct called START, which was a group of people who have managed defining and putting together a lot of science trades, not just for the exoplanet science, but also the general astrophysics, and then try to tie those back to the technology, so that as we did the technology road mapping, we knew what we were sort of needing to do all of the science that this telescope will do, so that that could be included in the tech development plans. Once we got the project office guidance from Congress, we had to basically disassemble that construct because of legal reasons. So what we have done is all of those working groups have now moved, and they report to the project office, but they are still doing their work. They're all working to generate white papers by the end of the year that will then be folded into thinking about how we move forward with the telescope. Our expectation is that later in FY25, we will put together a science and engineering definition team. I don't have an exact date for that yet, but that's the overall plan. And that team will take all the work that's been done by the working groups and start to fold it into the initial set of requirements for this telescope, and make sure that the requirements as we go forward match the technology development that we're doing. So I'm going to finish up there and take questions. We have a website now, so if you want more information on the Habitable Worlds Observatory, we have a website. We also have a community Slack, and you see here a list of interested people that you can contact. Now, we have a lot of interest from potential international partners. We've obviously spoken to the European Space Agency. The Japanese Space Agency are also very interested and kind of committed to going all in at the SPIE meeting a few months ago. So there's a lot of international interest in this program as well. And we really, at this point, welcome all comers and trying to make sure that we're as inclusive as possible in getting ideas via the working groups and partnerships, or inclusion via the international partnerships. So I will finish there, say thank you, and take questions.
So we got a question from Zoom. So from Elizabeth Tasker, she said, amazing missions. The search for biosignature is obviously of huge human interest, and the successful detection of a possible biosignature will cause a lot of global excitement. Is there any outreach program in place to plan for how this information will be released to ensure accuracy and understanding across all the communities and public who will be interested in?
So the question was, is there an outreach program, and how are we getting information out to the community? So first and foremost, as you see here, we have a website. One of the jobs of the project office, which is located at the Goddard Space Flight Center, is that they put together an outreach program that will operate together with the project office to make sure we keep people informed and also up to speed on how things are progressing with the program. When there are calls for committees or membership, such as a science and technology definition team, that will all come out through the project office and their outreach program.
Yes, the coronography with a desire to get down to 10 to the minus 10 is a real challenge,
Yes.
obviously. My question is, to what extent has an external occulter been considered for coronography?
So we looked at the options going at the beginning when we were figuring out how we wanted to proceed here. And I guess I'll say a few things. First of all, we started this relatively late in the decade, the pandemic being the primary reason. And so we wanted to move forward as quickly as we can. And we felt that building on the technology that we already have and are already developing was the best approach. I will just say, having come off of the James Webb Space Telescope, NASA has a very significant level of experience doing large deployables. And for this particular mission, you're talking about a 60-meter large deployable with, again, just as difficult tolerancing and alignments. And we've learned the hard way on James Webb that getting those tolerances just right on large deployables is challenging. So we decided that we build on the technology that we have spent the most on in terms of investing the taxpayers' money up to now, and that's coronography. And I'll just note also, Jeff, that even in the HABEX study, the core of the HABEX was still a coronagraph, and then you flew the Starshade. So I think there's general agreement that that's the order in which you do it. I certainly think in the future, for a second generation, flying a smaller Starshade, especially for the ultraviolet work, would be a great way to go. But I think getting more experience with large deployables is an important step along the way, and that comes at a pretty significant cost. Thanks.
Thank you very much. Can you show again your slide about the biosignatures? I mean, the one. And I was wondering, if we look for something like Earth 2.0, we know that we have a lot of nitrogen in our atmosphere. Is there any feature that exists which could actually detect nitrogen?
I'm probably not the right person to ask about that. We have people in the audience like Dave Charbonneau or Nicole sitting over there who can probably better answer that question than I can. So I encourage you to speak to them at the end of the session.
Okay.
Yeah.
Thank you for that great talk. Could you comment quickly on the servicing aspect?
So the idea is that we probably will want to do more than one generation of instruments to do this science. And robotic servicing seems to be the obvious way to go. Now, if at NASA, we see a lot of interesting commercial companies right now who want to be a part of Artemis. And there are at least 3 or 4 companies out there already building things they call space tugs, which are essentially spacecraft with massive fuel tanks and big robotic arms for doing things like cislunar logistics. So we want to leverage the investments that have already been made and use that to do robotic servicing. Obviously, there's going to be artificial intelligence required to do that, but these companies are all developing those capabilities. So why would we not use them?
A follow-up from Elizabeth Tisker about the first question. She means that whether there is a sensitivity of releasing this information about the biosignature had been considered to avoid any inaccuracy and type.
Sorry.
So her first question about is there is any outreach program to release the information about what is the possible biosignature was considered in your program. Now she's following up that asking that whether there is any there is like a sensitivity of releasing information about the biosignature that has been considered in your program to avoid this misinformations.
So the question is, what information is there on biosignatures and how to access that? And I would, we have a whole working group looking at biosignatures, which is why I probably am not the right person to comment on individual lines. But I would encourage the questioner to make contact with that particular working group that's looking at this issue and the science trades involved. And that's all online at the Habitable Worlds website. You can find any of the working groups and make contact with the people in those working groups.
Hey, thanks everyone for coming. Dr. Chima Magruder, and I'm presenting my work on exploring correlations of aerosol high altitude aerosol formation in exoplanet atmospheres. And so this is the work that I did as part of my thesis. So I'm trying to condense all of that in 15 minutes. So let's just go ahead and get started. Okay. Just a quick overview of what I'm going to be discussing. First, I'm going to talk about the problem of aerosol formation, high altitude aerosol formation in hot Jupiters. Then I'll talk about the specific technique I've used to address this problem, particularly the twin sample, the results that I found, and then I'll talk a little bit about what I'm doing currently. All right, so firstly, aerosol formation in hot Jupiters. So aerosols, which are defined as clouds and hazes, they affect the atmospheres of the planets that we observe pretty much ubiquitously. Recent study has found that around 93% of atmospheres are affected by aerosols. And you can see this effect in this model spectra right here, where the blue is what the transmission spectra looks like without aerosols, and the purple is when it's 1/3 muted by aerosols. And that the average effect of these aerosols affecting the atmospheres is about 1/3. So essentially, aerosols affect all atmospheres of exoplanets, but they don't affect them equally. And you can see this here from the top. This transmission spectra is relatively clear, where you can see strong sodium-potassium lines and water in the near infrared, suggesting that there's not a strong level of high-altitude aerosols. Whereas if you go down to features down here for WAS12b, the features are almost completely muted. And then you have situations like this where the most of the features are gone. You see a little hint of water, but really the only sign that you see here is the strong scattering slope due to hazes. So it's important to determine, it would be useful for us to determine which atmospheres, a priori determine which atmospheres have aerosols and which don't, because then that can allow us to optimally use our telescope times, such as James Webb, the next generation of ground-based telescopes, and et cetera, and well plan our observing strategies. So for this reason, there's been many attempts to try to find correlations with clouds and hazes, so aerosols, but then there has yet to be a concrete correlation found, because all of these studies have approached it differently, and no consistent trends have been identified. All right, so then that brings to the method that I did for my thesis, the twin sample technique. And yeah, what I like about this approach is we identified 7 planets that have all very similar characteristics to one another. And the benefit of this is it's essentially, yeah, in space you can't have a control sample because it's not a lab that you can control. But when you specifically identify planets that share most of their parameters together, it's effectively having a control sample, where only one or two parameters differ from one another, and you can use those few differing parameters to isolate correlations in your sample. So that's exactly what I did with these 7 planets listed here. And to ensure that the sample really were twins, so all their parameters were, or most of their parameters were truly similar to one another, we used a wide slew of data to confirm the planetary and stellar properties of the systems. This was with, we used space-based data as well as ground-based data to do this. So after refining, using all this data to refine the observations of the system parameters, we then ended up with this table, which my systems are blue, red, and teal. And as you can see, a lot of their parameters agree very well with each other. So equilibrium temperature, planetary gravity, radius, the planetary density, insolation, all really tightly knit together, very similar. And the only parameters that are different from one another would be the metallicity and the high energy irradiation, which is parameterized by the RHK value and the luminosity, UV luminosity. So essentially what we have now is we have a sample of 7 planets that have their parameters, their stellar parameters, planetary parameters have been refined to show that they are indeed very similar to one another, except for a few specific parameters. And their transmission spectra are different from one another. So before this survey started, or this study started, there were 3 planets that were observed, WAS6, 96, and 110. And they have very different transmission spectral features. You can see WAS 96, it has a strong sodium feature, water, and strong water features. And so at least in the optical, it doesn't have a strong suggestion of higher altitude aerosols. Whereas WAS 6 is somewhere in between, where it does have sodium and potassium features and water features, but they're muted and not as strong. And WAS 10b is on the other end of the spectrum, where essentially there's no features to write home about. So yeah, we have this sample that has shown that the transmission spectral features are different from one another, but most of the parameters are very similar to one another. So then the point is to understand why and see if we can isolate from one of the 2 parameters that differ a trend. And yeah, so yeah, let me move on to the results that I found. I found from observing 5 of the transmission spectra, I found a tentative correlation with metallicity and aerosol formation rates. So the aerosol formation rate is parameterized by the sodium feature. And I say this is a tentative correlation because, as you can see here, the error in, for example, WAS 124 is pretty large, as well as 25, and WAS 55b and HATS 29b have yet to be observed. But this is suggestive. It's very suggestive. And so let me just go a little bit to explain possible reasonings for this correlation. Okay, so to form high altitude clouds and hazes, we think that you need seed particles for the clouds to condense on. And given that the metallicity of the host star is correlated to the metallicity of the planet because that they grew in the same field, then when you have a higher metallicity, the overall weight of the seed particles is heavier, and then it's possible that it would sink down deeper into the atmosphere. And so when these seed particles are sink down deeper in the atmosphere, they would still form, still could form aerosols, but they wouldn't be as suggestive in the transmission spectra. Whereas when they have a lighter, or sorry, a lower metallicity, then the C particles would be lofted higher in the atmosphere, and the aerosols would form at higher altitudes. So this is what the a theory that could explain this, and this is the data is supporting the observed data so far is supporting this. Yeah, whereas these are the same figures as before, but they're now on the same plot. Essentially, that the planets with lower metallicity could then, their C particles would be lofted higher in the atmosphere, and then they would have higher levels of high altitude clouds and hazes, and then the opposite's the case for particles with planets with heavier metallicity. Okay, and I think one of the slides that I had didn't end up on here, but I did these observations through the Axis collaboration, where we use the Magellan, one of the twin Magellan telescopes, SPADA, to observe the transmission spectra of these telescopes, of these planets, I mean. Yeah, okay, so just quick takeaway of what I've presented here is that, yeah, aerosols affect pretty much all exoplanet atmospheres. But what exactly is controlling these, what specific parameters is causing these aerosols to form is unknown, but being able to identify a priori parameters that are correlated to aerosols would be extremely valuable for telescope usage and time optimization. And so for this end, we found a sample of 7 planets where I've observed 5 with the transmission spectra, and homogeneously characterize all of the planets to isolate metallicity as a correlation with aerosol formation rates. And so I want to end with the stressor that this approach of using targeted planets to find correlations in system properties, observed properties, is a unique idea that can be now applied for other properties that you're interested in, not just aerosol formation rate, because we now have a wide slew of planets that we've observed, or sorry, a wide slew of planets that are available, and we can make control samples with these planets. Okay. And yeah, so I just so I did this work, finished it last year, 2023. But I want to just do, if you allow me, just one slide to talk about the stuff that I'm doing now. And this is, I'm in the process of switching actually from astrophysics to environmental science, climate science, however you want to call it. And yeah, I want to just provide one slide on the work that I'm doing related to that. And so I'm doing this work with a collaboration of a couple other scientists who are also working in this transition. And essentially what we were trying to do is help improve the discovery of materials. Essentially, the development and discovery process is 15 to 25 years, which is way too long for if you're talking about in environmental scales. And so we're aiming to speed that up by at least 10 times. And the solution that we used is a solution that I think everyone in science is using for everything, machine learning. And the approach that we're doing it, the specific target case we're doing this for is photovoltaic material. But this approach can be used for other types of materials as well. And just a quick rundown of how this process goes through is we're using a crystal graph generative adversarial network, a mouthful, but basically it's a machine learning technique to predict or produce new material. And then the second stage of the machine learning is a new machine learning technique a different machine learning technique to predict the properties of the material, whether it be conductivity, durability, flexibility, etc. And then the final stage, which is beyond where we're at now, we're just focusing on the machine learning aspect for now, but then to be to properly test these in the wet lab. So yeah, that's what I'm doing now. And I guess I'm over time, so thank you.
Hi, Engin Kielet, Freie University Berlin. Nice talk. Having in mind that the potassium and sodium lines have very similar photoionization and condensation properties, could you also do the same thing for the potassium amplitude to check if you see the same correlation?
Yeah, so we specifically did sodium. Yeah, it was more of a strategic decision of that because some atmospheres have potassium lines, some atmospheres have sodium lines, and some have both. So they're not. I think this is. I would say that this is why some have sodium lines, some have potassium lines, and why the relative strength between them is different. Is still under investigation, but I think such study could be done with potassium lines as well. But we specifically chose sodium lines just because of the data set, and we wanted to have just one feature that we were focusing on. But yeah, I think doing a similar study with a different optical feature is very possible.
Okay, good afternoon. It should come up. No? Yeah. Okay. So while we are in this session of James Webb, where I think this model would be of interest for many of you. So this is a model that would extend the habitable zone and the possible targets for a biosignature much outside the conservative habitable zone. And before telling you something you probably know, I'll go very quickly about the habitable zone. I'd like to advertise a book that is now in Springer. It will come out in a few months, and it has all of this and much more about astrobiology. As you see, the subtitle is Astrobiology for Non-Scientists. And this is a summary of our coursework of about 25 years, me and my colleague, for teaching astrophysics and astrobiology for exactly students of the humanities. I have a few flyers here, and there are more in the Springer booth downstairs, the exhibition. But let's get to business. So the habitable zone of the solar system is well known, and we know that in exoplanet it depends on the main sequence type of the star. And here is a quick summary of it in graphic forms. So you see that the solar system is a stars of about 6,000 degrees stellar surface temperature. Earth lies nicely in the middle of the green area, which is a habitable zone. And the nearer stars are too hot planets, and outer are too cold. So this is a kind of the conservative habitable zone. And we also see that the stars that we'll focus about, I think, yeah, here, red dwarfs lie in much cooler temperature, and consequently, the habitable zone is much smaller physically. But this is another way of presenting it, also a well-known figure. So we have the solar system here at G-type stars, one solar mass. But and this is the habitable zone, the classic habitable zone, which depends on distance, of course, and the stellar type. But if we are looking at the summary of my talk or my work, we are extending it in two ways. One is for closer planet, nearby planets, which are in this area. And one is for outer planets, which are supposed to be too cold to have liquid water. So maybe I forgot, but it's obvious in this session that habitable zone is defined by the presence of liquid water on the surface of a planet with an atmosphere that can support it. But what about habitability under ice, for example? So we'll get into it. So as it maybe sounds strange, hot locked planet can support even hotter than this equilibrium temperature of boiling temperature of water. And also on the other side, we have this extension. And we know in the solar system, for example, we have some moons of Jupiter and Saturn that have indeed subglacial oceans, and even biological molecules have been detected. And if we are going to, as I hinted before, to red dwarfs, there are many advantages for exoplanet detecting and even biosignature detecting. So in particular, the planet is closer to the star, all we know, than shorter period, more transits, etc. But also the ratio planet to star is bigger, and this lets also easier observation of transmission spectra. And here is just for an image how Earth would look if it would be gravitationally locked to the sun. And of course, we have famous systems like TRAPPIST-1, but we have here in tidally locked planets have a much large temperature differences between day and night sides. And I demonstrated this in an UpJ paper from 2018. Red dwarf stars, they have, because they are locked, they are having here a substellar point, which is much hotter than the rest of the star and much colder here. So we can define already a somewhat extended habitable zone by defining the outer temperature as being the one here where even the substellar point has barely liquid water, and the inner point is where even the night side has almost boiling or almost evaporating. But let's go into the real subject of this work. Habitability and subglacial liquid water on planets of M-dwarf stars. This was a subject of a Nature Communications paper. And the essence here is we have to have a little closer examination of the habitable zone and this dependence on stellar type. So we see this is a conservative, this is a little more extended habitable zone, but still the traditional one. But if we present this not as a distance from the star on the horizontal axis, but as a function of flux, we all know also this figure, of course. So we have here the conservative habitable zone and the little extended, more optimistic habitable zone by the inner zone by recent Venus and early Mars. But we can extend this even further. And what we do for this, we look at I'll soon get into this. This is the two dashed lines. This one extends this inwards, and we can extend it even more. This depends on the transport, on the atmospheric transport of the locked star. And we can extend it outside by considering, for example, the Martian polar lakes, which give you some experimental outer limit for the minimum flux that is needed to keep subglacial water like the Martian lakes. And here we have the tidal locking limit. So all planets here under this curve are tidally locked. So this is also somewhat known, but in a new form, this can be presented like this. So here we have, again, the same, here's the horizontal axis is inverse. So here are the low flux planets and the cold planets. This is the habitable zone, the traditional habitable zone. And this is recent Venus. And see how much more we can extend this habitable zone inwards if we consider subglacial water. It's a little contradictory. How can we have ice on locked planets which are too hot. But actually, you can have ice on the night side. I'll get to it in a moment. So here you see some limits. It depends on how much the night side evaporates due to atmospheric transport. If you have, for example, 30% of the energy in any point transported homogeneously around the star, you will have ice evaporate at this kind of radiation. This is the flux that Earth receives. This is 10 times the flux Earth receives. And here are some well-known examples. Here is the TRAPPIST family. So TRAPPIST B received almost 6 times or 7 times the amount of Earth. And this is the other side, the outside range for very low installation. So this line is set by the Martian polar lakes. That is how little we can still maintain subglacial liquid water. Well, this is well known. This is just to explain about transmission spectroscopy, but these are some examples. Transmission spectrum of TOI 270D has been presented by Nico already earlier this year. And the question is, could water and biosignatures be detected on hot, locked, rocky planets, which should, by some researchers, not have an atmosphere, not have water, because their hot, their red dwarf host has this strong UV and stellar flux that could evaporate the atmosphere at the earlier phases. And water actually could survive under ice on the night side, as I hinted before. And actually a similar situation could exist not only on a I wanted before. No, it could exist not only on a TOI 270D, but also on the B star, and on this also quite high flux exoplanets that would otherwise not be considered for liquid water and biosignatures. And also in the TRAPPIST-B family, TRAPPIST-1 family, there's some evidence that this does not have an atmosphere, but maybe it has, so we could examine it. And all these planets here, and many more, of course, I didn't show all of them, are beyond the tidal lock boundary. They are tidally locked, and therefore they may have ice on their night side. And on the other hand, of course, we have a TRAPPIST-1 H, which could be beyond this. So it could have subglacial polar lakes like Mars and still have liquid water. And this is, if we considered all these factors, we could incredibly increase the number of exoplanets that could be available for observations of James Webb and further telescope for biosignatures. So for example, if we look at the conservative situation, this curve here, we look only at G stars and only in this amount of habitable zone. I won't go into details. So at a distance of some 100 light years from Earth, we could expect about 100 planets, exoplanets, which would have in this habitable zone. But if we consider the somewhat extended, so G plus K, it would be this curve. And if we go to the extreme, to the M dwarf and the greatly extended habitable zone, you could have within 100 light years as much as 10,000 planets. So this is really dramatic increase. And I only have 3 minutes. Yeah, so we need only 1 minute to read the conclusion very fast. Red dwarf stars may have an extended habitable zone due to tidal locking of their habitable zone planets. Liquid water may exist under ice layers on cold rocky planet due to basal melting and geothermal heat. That's some Nature Communications papers that have been in 2 years ago, showed this. Extending the habitable zone inwards, that is night side and locked planet with low heat transport. That's what I said about the 30%, 10%, etc. This would extend the habitable zone in a great amount on hot planets close to their host star, extending the habitable zone outwards. So subglacial lakes and geothermal heat would extend it greatly outwards on cold planets. And this may enable the detection of water and vapor and biosignatures on hot Earth-like red dwarf planets closer to their parent star. And we may use James Webb to see if this is really present. Actually, some of these candidates were already found, and not very certain, but there were water vapors in the spectra, in the transmission spectra found where they should not have been, according to some works that said that red dwarf planets could not survive with an atmosphere and water. And including, finally, the final graph, including red dwarfs and extendable habitable zone, enhance the number of potentially habitable planets by up to a factor of 100. Thank you.
Yes, we got a question from online. It says that if life exists under a frozen crust of a night side of a tidal locked planet, will there be enough of an atmospheric signature to be detectable by transmission spectroscopy, as the ice slide would prevent strong atmospheric coupling?
Yeah, if I understood it correctly, how would we discover a biosignature if the ice layer isolates the water from? But this, one of my first slides was a cartoon of Enceladus or Europa, and we know that are these plumes. So the ice layers are not hermetic, and there are, if there are some cracks or by other means, they would be transported to create a thin atmosphere above the ice.
Thank you. All right. So I'm going to be talking about the importance of ground-based transmission spectra in characterizing stellar activity for James Webb. So to start with, I have a little explanation that you've probably already seen today about what transmission spectra are. I've used here the cover of the special Nature edition for the ERS Transmitting Exoplanet Spectrum program. And you can see very nicely that there's this star and the light is coming. Part of it's being blocked by the planet and it's made it to the telescope. And the telescope is looking at all of these different wavelengths. And in every wavelength, you can look at the transit, see how much light is blocked. And if the atmosphere is opaque, then the planet will block more light than if the atmosphere is transparent. So we can turn these measurements into what we call transmission spectrum, where we're effectively looking at the effective or apparent size of the planet as observed through transit. And this means we can see features of atmospheric absorption in those spectra. Yeah, but the part I want to talk about specifically right now is a rather small part of this picture, but it's still a very important one. That's the star. And that's because in this picture, we have a very nice star. It's very even, it's quite bright. And it's basically our perfect model star because it's a uniform disk. But how realistic is that really? Because we tend to assume that this is the case. But a lot of the case, we can have various kinds of stellar activity. So we can have sunspots or star spots that can be a couple of hundred to a couple of thousand Kelvin cooler than the rest of the surface. We can have bright areas that I'm going to be calling faculae, that can be a few hundred Kelvin hotter. And especially on late-type stars like M dwarfs, where we do a lot of looking for biosignatures and things, we can have actually quite a lot of activity. And the reason that matters is what we tend to call the transit light source effect. I have here this black line is the transmission spectrum of a planet with no atmosphere. So it's constant with wavelength. But I also have here a star with some bright areas outside of the transit chord. So even if the bit that the planet is transiting is very nice and smooth, these bright areas are still going to have some effect. Because what's happening is that the part of the star that is being blocked by the planet is lower than average brightness. So the planet is going to appear smaller than it would otherwise. And this is because of the contrast between these hot regions and the rest of the star. And this contrast is wavelength dependent because it depends on it's a black body with temperature, right? So the regions are hot, the contrast is larger at short wavelengths. Similarly, if we have dark regions instead, if we have star spots, then suddenly the path that the planet is covering is higher than average brightness. And especially at short wavelength, we see this increase in the observed planetary radius. And it's not just that we get this slope, which you might see looks quite a lot like the aerosol signatures we saw earlier. We can actually also get false positive molecular signatures. So especially if a star spot has water in it, this can lead to the observed spectrum having a fake water signature. This activity can also impact the size of the sodium feature. It can lead to false positive TIO. There's a lot of things that can be hard to tell whether, well, that can look like planetary signals, but that are actually stellar signals. And then, of course, to make it even more fun, usually it's not one or the other, it's a combination of both. And we can model this. And especially for James Webb, you might say, well, does it really matter? I mean, it looks kind of like it's evening out, right? Like there's a little bit of an offset, but it's not doing much. Because James Webb looks at longer wavelength and the contrast is lower there, so the effect is smaller. But the answer is yes, actually it does matter. And I have here two transmission spectra of the transiting planet TRAPPIST-1b. You've heard it a few times today already. It's this famous planetary system, 7 Earth-like planets around an M dwarf. And these are two transmission spectra that were observed at different times. And you can see they look completely different. And that is entirely due to unocculted stellar activity. So all of the signal that you're seeing, all of these bumps, these slopes, it's all stellar activity. It's not the planet. And in this case, they were able to model that. There's a little bit of short wavelength information here, even though it's not a whole lot. So they were still able to say something about the planet. But here's another example from last year, GJ486b. Has also already been mentioned a few times. It's an Earth-like planet around another M star. Actually, you've already seen this plot if you were here this morning. And this has been observed in the G395H band with James Webb. It's a very popular band for planetary transmission spectra. And you can see there's this water signature, right? Except there's two ways to explain this signature. One is that there's water in the planet atmosphere, that's the blue one. The other is that the planet has no atmosphere, and the water signature is entirely due to unocculted stellar activity. So that's this orange line, right? So fortunately, they're going to be getting some optical information. But what this really shows you is we need these optical wavelengths. We cannot distinguish between stellar activity and planetary atmosphere if we don't have them. So I want to show you some optical wavelength for another James Webb target, specifically WASP-69b, has already been mentioned as well as part of the Manatee program. A few years ago, it was part of the NAME ExoWorlds program, was assigned to Cameroon. So I figured since we're in Africa, it would be fun to include that. The star was named Wuri, which is the largest river in Cameroon, and the planet was named Makombe, which is one of its tributaries. Now, the star is a K star, so you might assume it would be quite active. It's a little bit smaller, it's a little bit cooler than the sun. And there's actually been some discussion about how active this star really is. The planet is very close to the star, so as a result, it's very puffy. It's got a large radius, it's almost the size of Jupiter, but it's not very massive. And this is actually good for us because the larger the atmosphere, the puffier the planet, the more signature we actually get. So that means this is a planet that's relatively easy to observe. And it's also quite hot. It's nearly 1000 Kelvin. So like I said, it's part of the Manatee program. It's also part in transmission in the 395H band that we just saw of another James Webb program, 3712 over there. And that means this program does not have any optical wavelength included in the observations. So we looked at this target with VLT2, with Force 2 on the VLT. And we looked specifically in 3 different bands. We used Force 2 is a multi-object spectrograph. So we looked at both the target and the reference star. So you see these more solid lines, that's WASP 69. And then the fainter ones, that's the spectrum of the reference. We observed over 3 different nights in 3 different filters. So we would get full coverage of the optical wavelength. And so full range of 300 to 1100 nanometers. We did this in the MXU mode, and additionally, we got simultaneous photometry from the Euler 1-meter telescope in La Silla. This is interesting because VLT is in Paranal, Euler is in La Silla, so anything that we see in both is astrophysical, not weather or anything else. All right, so first we look at the wavelength integrated light curves, so what we call the white light curves for each night. I've got them here in chronological order. So the first one, we see there's a bit of correlates, noise, nothing too special happening. The second one already has something a little bit interesting. It looks like a spot crossing. Unfortunately, it's about the same amplitude as the noise. We couldn't confirm it in the Euler data because the weather was quite bad at La Silla that night. So we'll ignore that one for now. But especially interesting is this dip in the third light curve. So this is kind of doing the opposite of spot crossing. It's a facula crossing. So while the planet is crossing this bright region, it's suddenly occulting more light than usual. And we can see this in the Euler data as well. So here we have the Euler light curve and the Force 2 light curve. We see the same dip in the same place. And we think that that is because of this bright region in the path of the planet. Usually these kinds of observations are a bit tricky because there's a degeneracy between contrast and size of the region. So you could have a very small, very bright region or a very large, very faint one. Fortunately, because we're observing in 2 different wavelengths here, and we're looking at the same region with the same temperature, we can use that information to break the degeneracy. So what we get is about 600 Kelvin hotter than the photospheric temperature. This is a bit hotter than you might expect, but it's also quite a large error bar, so a little on the high side, nothing too strange. And if we look at the transmission spectrum, I'll just go from blue to red here. We can see on the blue side, this very characteristic drop in planetary amplitude in transit depth. There's a couple of points here that are a bit messy. That's a detector sensitivity issue, so you can ignore those. But if we do a joint retrieval of stellar parameters and exoplanet atmosphere, then we can get a temperature for this facula contamination. And we find that these are about 200 Kelvin, which is very much in line with previous observations of facula contamination and what you would expect theoretically. Also better error bar this time. And also more or less consistent with the slightly higher temperature we found for the facula crossing. So I think we've definitely confirmed here that there is a lot of bright regions on the star during these observations, and it's definitely active. In the middle of the spectrum, there's not a whole lot to see. There's one point that sort of stands out. That's the telluric oxygen band, so you can ignore that one. And the region you're not seeing very much there is essentially because it's cloudy. The clouds on this planet are suppressing all of the other atmospheric features, except for this rise at the red end, which our retrievals attribute to water and ammonia. Both of these show kind of increase in absorption towards red wavelengths. It's also worth noting that both of these molecules are consistent with previous observations, and actually the abundances we get are consistent with from-scratch atmospheric chemistry modeling as well. So to summarize, WASP 69 is an active star There has been some discussion in the literature about whether there is any activity or not. It is. So for the James Webb observations, I would highly recommend getting some kind of optical information. We directly measure the temperature of a bright region on another star. It's a pretty rare occurrence. It's about 600 Kelvin. We indirectly measure the activity temperature through the spectrum contamination. Again, about 200, slightly lower, but within the error bars, fairly consistent. We detect sodium and ammonia. We detect these very high altitude 1.4 millibar clouds that are muting all of the other absorbing features. And we put some upper limits on some of the other atoms where we couldn't determine the features. But most importantly, I think, is that we show that by determining this activity, getting this information from the optical wavelengths is crucial to understanding what our James Webb data is telling us. We need to be able to distinguish between these different scenarios, and optical wavelengths can help us do that. Thank you.
Right, so thank you for this most interesting work. Yeah, actually, GJ 486b was the inspiration of some parts of my works that I showed before. And my question would be, could your technique help to break the degeneracy on planets like this, which are small, so it's more challenging, rocky planets?
Yes, absolutely. Obviously, the smaller the planet, the better the observations need to be. This is a very nice planet because of big atmosphere. But I think there have been optical transmission spectra of some of these similarly sized objects, like GJ 1214b is also an Earth-like planet, has also had an optical transmission spectrum. So if you can get the right telescope and the right time, then you can absolutely do that. Thank you.
Hi. Hi, folks. My name is Engin Kilis. I am a postdoc at the Freie University in Berlin. And I would like to tell you something about high-resolution transmission spectroscopy and how we can use this to probe lava vault atmospheres to get complementary information to JWST. And stay tuned. I guess today you will see the highest signal-to-noise transmission spectrum acquired from ground for a rocky planet. Okay, let's start with the basics. So here I am showing a small animation of a lava vault planet. And what are lava vault rocky planets? So these are planets which have molten surfaces due to their high surface temperatures exceeding 2000 Kelvin. And as you see on this on that animation, you have a quite thin, probably atmosphere on top of this envelope. And the first question is, what kind of atmospheres can we expect for rocky lava vault planets? So the first idea could be like, it's like molten rock, yes? So probably if we go to Earth, the bulk silicate Earth composition consists of a lot of magnesium oxide, iron oxide, silicon dioxide, which gives us a mean molecular weight, if you put all this together, of 48 grams per mole. So which is a very heavy atmosphere compared to Earth, yes? Earth has an atmospheric mean molecular weight of around 30 grams per mole. But must lava vault atmospheres consist of this composition? No, this depends a bit on the recycling efficiency from your interior of the planet, yes? Imagine you are increasing the volatile content in your planetary atmosphere by recycling efficiently volatile from the interior to the magma ocean. You could also get a CO-dominated atmosphere with less mean molecular weight, or even H2 or N2-dominated atmosphere. So what is good and what is bad for observation reasons? So if we would have a degas silicate atmosphere with a heavy rate atmosphere, this would be a bit bad, yes, because when the scale height decreases, it becomes more difficult to observe it. Other way around, if we enrich the atmosphere with volatile species like CHN, we will increase the scale height and make it easier to detect the atmosphere of a lava world planet. Why is this again important? So I will speak about this in the cross-correlation method later, but first of all, let's have a look to the samples of hot rocky worlds. Are there hot rocky worlds which we could investigate? Here I am showing a planetary radius or a planetary mass diagram with some selection criteria, like the whole star visual magnitude should be at 11, so we can get nice data, orbital period of less than 4 days, and planetary radius and mass up to super Earth. So if you apply this criteria, only 25 of more than 5,000 exoplanets remain. So it's not much, but which of them to observe? So to estimate this, what you can do is like you can calculate the transmission signal metric or also emission signal metric for emission spectroscopy. So this does not tell you which of the planets have an atmosphere. It only tells you if all these planets would have the same kind of atmosphere, which of them would be the best target to use. And this scales with a planetary radius and mass and equilibrium temperature, but also the host star size and host star brightness. And as you see here, especially 2 targets have a very high TSM signal. One of them, on the left-hand side, I am showing sputtering worlds, which have surface temperatures probably less than 2000 Kelvin, so probably not molten rock. And on the right-hand side, you can see lava worlds. And the TSM signal of one planet is significantly higher than of other planets, which is 55 Cancri E. So let's focus on 55 Cancri E. Probably all of you know this planet, which is a rocky planet of 2 Earth radii and 8 Earth masses. It's in super Earth. Its orbits on 0.7 days orbit, and the host star has a visual magnitude of 6. So it's a naked eye target. So you get amazing data. Yeah, I mean, it's always nice to observe this target. And from JWST perspective, this is a very interesting target because recently Hu et al. Showed the first rocky planet atmospheric detection, showing a carbon monoxide dominant atmosphere on this planet. Here you can see quite nice the carbon monoxide feature, and this is the result from one observation. Okay, it was a wow effect, yes. I mean, the first rocky world atmosphere detected. However, waiting a few weeks, Patel et al. Showed that 4 more visits of JWST could not confirm the thick CO band. Basically, you could fit the data with everything. Yeah, from planets with 1000 Kelvin to 2000 Kelvin with different atmospheric compositions. Even a black body spectrum was possible. So at this time, it's not that clear what kind of atmosphere 55 Cancri E has. So the question is, can we use high resolution observations from the ground to get complementary information to deduce if there's a CO atmosphere or not? Probably. To do so, let me introduce very quickly to high resolution transmission spectroscopy. It's a 20-second thing. So what you have here is a transiting planet in the blue box. And during the planetary transit, what happens is the stellar photons penetrate the planetary atmosphere. Some of them are absorbed, some of them are scattered. And what you in the end get is a planetary fingerprint. You combine all the data at the planetary red frame and you get one combined planetary spectrum. For gas giants, easy. Nowadays, easy. I mean, 20 years ago, it was not easy, but nowadays it's like you detect several amount of atoms and molecules in their atmospheres. But for rocky planets, difficult, yes. Imagining that an extension of a rocky planet atmosphere is like maybe 20 to 50 kilometers, hard job. So what we can do is we can apply the so-called cross-correlation method. So here I'm showing in red the combined planetary spectrum. On the left-hand side, imprinted with a planetary absorption. On the right-hand side, no planetary absorption. And what you basically do is you use different templates with different atomic or molecular species, and you search within the radial velocity field for the presence of this element. So, and what you then show is the so-called cross-correlation function. If you find the element in the planetary spectrum, you get a peat. If you don't find it, you don't get it. Easy, yes? I mean, detectability scales with the amount of lines and with the signal noise of your spectra. So now let's go back. Which of elements could we, for instance, look in a combined transmission spectrum of 55 Cancri E? And Looking again to a BSE composition, one element which has a lot of lines in the optical wavelength range is magnesium oxide. Yeah, and as you see here, its abundance is very high. So can we now use magnesium oxide to deduce if carbon monoxide is in the atmosphere of of 55 country E or not? One thing we can do is we can apply the so-called injection recovery method. So what you do is you create templates of magnesium oxide, or this can be done with any species or any composition for the lower atmospheres, and you derive them for different mean molecular weights of the atmosphere. And for high mean molecular weight atmosphere, you get a less extension of a template. For low one, you get a high extension due to the scale of the atmosphere. And when you inject it to your data and you apply again the cross correlation search for it after you derived again your transmission spectrum, doing all the steps and getting a peak again will again show you how you if you detect an atmosphere or not. And this way you can deduce the upper limit, the lower limit of atmospheric mean molecular weight. Now, this is theory, yes? So some of you might ask, yeah, but how many transits do you need? Do you need like 5 or 500? This makes, in the end, the most important thing out of it. So let's imagine the LBT. The LBT is the Large Binocular Telescope. It is the largest telescope in the Northern Hemisphere. If you combine both mirrors, it has 2 times 8.4 meter mirrors. Yeah, and there is a high resolution spectrograph mounted on it, PEPSI, which you can in 3 different resolution modes, 50,000, 120, and even 250,000, which makes it, by the way, the highest resolution spectrograph, I think, available. The optical wavelength range, does it work? And yeah, now, how many transits do we need if we use, for instance, the LBT to probe for a lower world atmosphere of 55 country E? So here I am showing on the y-axis the probed altitude and on the x-axis the amount of transit observations. And the dashed lines show the at mean molecular weight limit we can probe. For instance, if you have 12 observations, you can probe a mean molecular weight of 39 gram per mole. And if you have like 16 observations, you can probe even bulk silicate earth composition. 16 observations are not so much, yes? I mean, this is something which we can do. And now let's go to the observations we have for 55 country. So now the promised high signal to noise spectrum is coming around. So here I am showing 10 LBT observations combined for 55 country E. Yeah. The transmissions, I mean, if you are a bit familiar with transmission spectroscopy, this is insane. And also the spectrum looks this is the highest signal to noise spectrum, I think, which is like available. The signal to noise per pixel was more than 1,000 per single exposure. So if you are interested in what kind of elements we are looking in and what kind of results we got until now, come to chat to me. The research is still ongoing because what we are now doing is we don't use only the template spectra for 55 country E properties. We also assume cooler terminator regions, hotter terminator regions. We look for all elements you can imagine. But what you can see, for instance, at this spectrum at this point is at the sodium lines, for instance, there is no sodium, for instance, absorption, which you can see in the spectrum, which can be ruled out now. So one might ask now, what is now the inferred mean molecular weight? So with this data set now, we can rule out a mean molecular weight lower than 30 gram per mole, only using magnesium oxide. We even did not, we did it, but for this talk now, what you also can do, you can combine different templates and get even better upper limit values for a mean molecular weight. So the big aim of this project is, the project is called, by the way, HADES. It's cool. We need further 6 observations at the LBT to be able to go down to 48 gram per mole. So this is the black dots are the modeled mean molecular weight, the red cross is what we got now, and to go down to a really maybe sulfur dominated atmosphere or even a bulk silicate earth atmosphere. We got further 10 observations accepted at the LBT. So hoping that we have good weather, we will reach the 16 observations. And this will help us in the end to rule out or confirm the presence of CO by detecting or non-detecting several species. Hopefully. I mean, if we cannot do it with 16 LBT observations for such a bright star, it would be very sad. Yeah, that's sad. Okay. What are we also doing at the Freie Universities? We are coupling interior atmosphere models to understand the evolution of such planets, and especially the connection between the efficiency of recycling elements from the interior to the atmosphere. So this is a collaboration going on from the AIP, Freie University Max Planck, INAF, and LDS, where we really needed all of us to get the whole amount of observation time accepted. So the take-home message is JWST is amazing. We all know this, but we can also use ground-based observations to give complementary information for JWST observations. And yeah, thank you very much.
Hi, thanks for a very interesting talk. As you mentioned from the James Webb data, the atmosphere seems to be extremely variable, even on the timescale of about 2 orbits. So can you really just stack 10 to 18 transmission spectra? Isn't the atmosphere going to change in the meantime?
This is a very good question. I mean, before stacking them together, we also look in each individual spectrum for variation of stellar lines or something else. But this is a good question. However, how much can we trust one JWST detection if we see 5 further non-detections? I mean, of course, if variability is going on, this is a problem, but we need to try.
Yeah, but you're not just averaging out all of your variability if you stack too many together.
We are not managing out, this is true. But what is your solution?
I'm not sure I have one, but I'm just curious.
I have also no solution for this. I mean, even if you have variability, which can affect, of course, your atmospheres, but if you have a certain, I mean, for instance, for these elements with certain amount of absorption lines, which have several absorption lines, is the question, should your variability affect all of the absorption lines at the same time? Or if it's, I don't know. I cannot give a clear answer for it, I guess.
I guess that depends on what's causing the variability, which
Yeah.
I don't think we know, but thank you.
Yeah, I'm also, yep.
Hi, Engin, very nice talk. And so you are you are ruling out the mean molecular weight with the MGO. Are there any other molecules that in that 5,000 kind of Angstrom range have a lot of lines apart from MGO?
I mean, there are several. I mean, I did this now, I only showed this MGO, but there's also aluminum dioxide. We also try this out with atomic stuff. I mean, the problem of this, all these molecules is, of course, the line list. Yes, how good are they validated or not validated? And for MGO, it looks to be quite well validated, especially at the wavelength region. It was laboratory tested, but this is a big problem, of course. I mean, what we also do is like we are coupling atmosphere lava models now to see what could be the end composition, not only having one molecule. This is always the big question about this, yes. How good are your line lists? How good are your templates? And is the stuff you are doing really the reality or not? Yeah, you're right.
Yes, thank to the all speaker for respecting the time. Don't forget that we have a poster session now, and please be in the area of e-poster to continue discussion. Thank you all.
2.0 space mission.
Okay. Thank you. Thanks for the organization committee to remind us me to give the talk. So let me see what's going on. Could you note? Okay. Okay. So this is the mission. Now we are in the phase B. So we already enter the real mission, and this is a 9 institution been work on the engineering part of the mission. And of course, the mission also has over 80 institutions from the internationally and domestic, particularly in the science. So with the team is growing, and in fact, the people interested in joining science, very welcome. And in fact, we are work on the new version of the white paper. So hopefully, will be officially published next year to finalize our science study of the whole mission. As you heard today, this the JWC really done great job. Really now we are not only in the regime to understand the planets, but also atmosphere. Especially like a habitable envelope, and look for atmosphere transmission. And it's difficult, but it looks like it's really getting to the stage we are engaged to the next stage. Look for possible life. You might say, well, in this case, then why we want to do Earth 2.0? Well, this is the same with the HWO. The motivation what Mark mentioned early on. So it's human beings really want to see if are we the only the planet have the life, and do they have another planet like our Earth? And that's the real motivation why we started the planet search many years ago. And since the first planet around solar type was discovered 1995, and really our main motivation is really toward find another Earth. So it's hard, but it seems to be doable. And it's very the recent work show that we obviously to find another Earth, you can't find identical size. So therefore we define is the size between a 0.8 to 1.25 Earth radius. And that radius actually now having to be the transient observation show, and the transient follow-up observation show that they are all rocky. Actually, the Raphael give a yesterday talk show that. So therefore, this is the good news. So which means if we have another transit mission and to locate the planet size, between 0.8 to even to 1.3 Earth radius, they are most likely a rocky planet. So therefore, it could be the very good targets to look for life. And here, of course, is our everybody familiar. This is a landscape. We put the estimate of the mass against the period. You can see clearly the right now is our Earth is lonely. But you probably also notice the transit mission already really approach the Earth size. And the other part, outside part is macro lensing is actually pick up quickly, is also getting to cold side of the Earth size. So this indicate right now, that we know a lot about these, giant planet, super Earth, and sub-Lepton, but really the Earth size planet, terrestrial size planet, we know mostly the short period, but the long period and even the free floating planets, we know almost very limited. So this is actually the motivation for us to design this mission to go after these regions, to really study the most terrestrial size planet. And here, of course, the talk about the transit planets survey, we have to go with the Kepler mission, which is a wonderful mission. And this mission actually started with Brookie in 80s. It's really amazing. He proposed this idea, many years, and nobody listened until 2000, and it's been selected, and until 2009, it launched to space. This mission really go after the Earth-like planets around the solar type of stars as one of the major goals. And obviously, it proved to be really hard. And here, of course, the Kepler show you that in order to find Earth, you really have to get precision down to about a couple 10 ppm. So everybody know that. So that if you look at all this data, from Kepler early data, you see each data points. Here in this diagram show is they have light curve over 4 years. So they by doing the processing, you'll see the very clear very nice photometry data. And if we see some, small dips, then those more likely will be trended. But it tend to be harder, Of course, Kepler is really in space have this advantage. So therefore, with couple 10, even 100, ppm, so they can really locate some small planets, such as this one is a habitable planet, around the M dwarf. So you can see clearly the clear signal in the habit zone. And here, of course, this is we recently used our deep learning program, actually, by the way, use the Kepler data again, and we're able to even push the sensitivity a little bit better. And this paper will be published probably in a few months from now. And you can see the signal, you can pick up is almost a couple 10 ppm kind of signal, weak signal can be detected by deep learning and program. But this show you, if you want to find Earth-sized planet, you do need to push for a couple 10 ppm, like a 20, 30 ppm, this kind of level. So it's not easy. So that's why Kepler, we have with even the best mission so far, but still, fall short. Okay, here show you the Kepler, of course, one of the reasons why we haven't found another Earth is another challenge is, the instrument systematics, sometimes mimic just like real signals, like this one. Initially, we all excited about Kepler 452 as the, be as a, Earth twin, but later on is most likely is caused by the instrument noise. So this is tell you that to look for another Earth, really need a, longer term monitor with a very good, stability, and also, understand the stellar noise as well. So therefore, it's not easy. Okay, it's not easy. And so therefore, the Kepler is a wonderful mission. But on hand, of course, first of all, it discover so many planets in especially super sublepton. Those new population is dominant discovered by Kepler. But of course, in terms of habit zone, in the habit zone, and still, we fall short. And so so now we look back, why Kepler, fell short, to not discover that. Of course, we know one reason is because the 4 years, the mission, the reaction wheel failed, right? So therefore, not able to continue. That's one of the main reasons. But on the other hand, if you really go back to look at the whole mission, you'll find out there's other reasons. For example, the field of view, even though it's a 100 square degree, it's still a little bit too small. So number of stars, observed, monitored, and download, and it's still too small. And also the stellar activity, as we know, is is more than expected, higher, and that caused a lot of trouble. And plus, actually the design of the instrument also tend to be with higher noise and without noise, for example, which will show later, show how we can overcome all these challenges. And so that's one reason. So when we look into the Kepler, done great job, but fall short, then how can do better? So this is our Earth to Moon mission we try to do. First of all, we want to go field of view much bigger. Okay. So for example, Kepler is is 500, is 105 square degree. So we want to go with 550 square degree, much bigger field of view. And also we want to go deeper, so therefore, and to reach deeper than what Kepler can achieve, and also download much more data. That's the more important, download many targets. Instead of 170,000 stars, we want download over 2 million stars. So therefore we can have nodal data we can processing. So therefore we set our goal basically to go after another Earth twin. And hopefully we, with this kind of strategy, we can eventually can find them, right? And secondly, we can study the terrestrial-like planets, how they form, how they evolve, because this is still the mystery right now, because we don't have enough sample, especially on longer period. And beyond that, and our mission, we also want to go with, because we stare at the Kepler field and the nearby field, because our field is bigger. So therefore, at the same time, we allow us during summer times, we can point, we have another telescope point to the galaxy center. So therefore, we can monitor doing microlensing sometimes. So which means every year we have half a year with one telescope point to the galaxy center, and then we can do microlensing with a ground-based telescope like a KMT-net. So we can do the microlensing same times. So this will give us the range, the cover range from the 1 year period to all the way to 100 years to even to free floating planets. So this kind of wide range of the period. And here, of course, our field is overlap with the Roman, with a little bit, but with much bigger field of view in a 4 square degree. you can cover it. And here show you the the one thing I mentioned, Kepler, why we couldn't discover another Earth is, data, limited is a very important factor actually. So therefore, we learn a big lessons. So we will download data every day. We will use a fixed, antenna array. So we can every day we download about 700 gigabits. So therefore, download over 2 million star data for 4 years, or even the mission can extend up to 8 years, right? So therefore, and also we'll do the on sky storage, to go back to to download some additional interesting targets. And here show you the design. The design, you can see how we can achieve that. It's not trivial. And of course, we not use Schmidt design, but instead we use a transmitter design. So we can use a lot of lengths and with a correction. So it's not easy. The design, you see we have to use big calcium fluoride lens, and also use a 9 lens and with quite several aspect surface. So therefore, manufacture and is quite a challenge, but we should able to manage that. And also with temperature control. This is another thing we learned. The test did the same thing. With temperature controlled, is doing the help the precision. Okay. And here show you we also use a detector. Remember one thing, Kepler have the detector loss is very high, is 86 electron average. And now we try to use CMOS, CMOS detector with a very big array. And so the readout noise now we test is only about 4 to 5 electron readout. It's very low readout noise. So that's tend to be important. If it gains sensitivity, is eventually you want to, with no readout noise. Okay. And here show you how we can achieve the precision we want. If you want to detect Earth, and obviously you need like each 6.5 hours you need 34 ppm, and because Earth transit is about 13 hours, as you can see here. And if you decompose the contribution from photon noise, from instrument noise, from stellar noise, because stellar noise typically is about 17 ppm, and so therefore you need to be room for 10 ppm. It's like Kepler tried, but of course the Kepler, unfortunately, the instrument noise is eventually higher than expected. And here, of course, we learn from the lessons. So we try to keep the instrument noise below the 10 ppm, which I'll show you how we can achieve there. Okay. And here show you we did all the simulation. We learn, and so therefore we do a simulation from the sub-pixel response all the way to including all the instrument, stability and the response and the readout noise and all kind of you can measure it. We all put into the simulation and to see eventually how good we can achieve the precision. And in order to show this method working, we actually go with the real observation. We use the real Kepler data. We measure the Kepler performance and behavior and put it into our simulator. And we basically reproduce what statistically show in their measurements. So therefore, these are our the real measurements, and these are our simulations. So basically, we can reproduce their measurements. So this will give you the confidence. You include all the factor, which is already done by Kepler wonderful measurements. So therefore, we can repeat these measurements. So we give us guidance about how to build a more stable instrument. And here show you again, if you zoom into from the 10 ppm to all the way to 100 ppm, those are the range. Eventually, we'll look for small planet. And you can see it here. We basically now we can simulate with through the thousands target that we simulated. You see our performance statistically very much reproduce all the measurements from Kepler. And then we use the same kind of simulation and apply our performance and of the instrument and can see what the ET looks like. It can do a slide better. And here show you might be easier to see what's going on. And you can see here in terms of field of view, we mentioned we are about 5 times field of view. And then if we talk about the sensitivity, we are about the 0.8 magnitude because the readout noise is much lower, right? And so therefore we can gain another a factor 2 of the target numbers. And but even more important, as mentioned, we are download over 2 million targets and data. So instead of 170,000, we do over 2 million targets. So that will give us eventually capability. These all together give capabilities about 10 to 15 times. So therefore, if we feel that Kepler is just short of discover another planet, and we actually now predict we should able to on order discover maybe on a 10-ish of the Earth-like planet. In fact, we actually use our simulation. We simply reproduce the Kepler's observation, and pretty much reproduce what Kepler discovered on the order about over 2,000 confirmed planets. So we use the same kind of simulation code, and we simulate our ET simulation, eventually produce our prediction with the transit alone. But then with microlensing, we should find another couple hundred, the Earth size, those cold planets and the free floating planets. So therefore, we should be on order to discover about 4,000. And here show you the error budget, how we can do better precision. Okay, so it's not magic; it's just the way you have to consider everything. First of all, we control the radar noise and get no radar noise, and then we consider all radiation effect, all kinds of things, and also control the temperature, make the imaging size. As you probably see the Kepler imaging, the breathing, go big and small, and we try to control the temperature, make the imaging, changes relatively small, and also control the scatter light, also control the telescope jitter and the thermal drifts, all these things together. And our current budget is we achieve maybe 7.7 ppm, and better than what we would like. And here show you the simulation. With 6 telescopes, you probably see each independently. They dance around. You probably notice jitter around. And then with the 3 days, we put a momentum dump. We put in, the telescope have to be readjust the position, and you can see move the imaging, around. And you see the photometry, the individual light curve is very different from each other. But we can do just like a test. We can do the co-trending and add together. You see here, this is what eventually for 12 magnitude like Earth-like planet, we can, basically, we can recover the signals. And this is, by the way, these measurements these are all the real PSF from the optical design. So we will consider all the factors and put it into the simulation. Show you this is performance can do. And here show you, you may say, well, CMOS is never done very high precision before. And for photometry, and can we do that with space? Well, that certainly will have to be proved. So this is the one we did in the lab. We actually do similar thing as what Kepler did, and use the transit hole and with tungsten line to heat it up, and then you can see see if we can recover the signal. You see here, this is what we did, and without transit, and you'll see we'll get about 7 ppm, and in terms of the reference. And include photon noise as well. And here with the transit, when we heat up the tungsten line, and it expanding, and then eventually cause about 40 ppm, and deep, and we can recover that. So basically, show you the CMOS has this kind of capability, and to do similar thing as the CCD, but also avoid several problems like CCD, radar noise, and also the CTE or other effects. And also, by the way, we already tested with the CMOS, the radiation tolerance is better than CCD in that regard. So here and beyond that, as we know, the one thing we learned from Kepler, not all stars are quite active. They're more active. 2/3 of stars are more active than our sun. So therefore, they produce a lot of noise. And in fact, we studied over the past few years, and we even get paper published now. We use Kepler data and photometry data, and plus our stellar activity from the LAMOS observation. You see clearly, and there's only a small percentage of the star. They are stellar noise below 20, 30 ppm. Those stars can be used for for Earth-like planet detection, but majority stars are quite active. They are not good for that. So therefore, we now already got the time, and on this wonderful facility in China called LAMOS, with this wide field and 4,000 fiber, we can position and doing the spectroscopy with 2,000. So therefore, we can our goal to for over the next few years, we can search 75,000 FGK star, and hopefully secure on order about 25,000. They are radio quiet star. Those will be our major target for look for Earth twin. Okay, so that will give us a chance. As we know statistics, if the Earth 2.0 is happen to be 10%, then we should expect maybe discover on the order about 10 of those. And of course, here show you the movie about the mission, and just give you the sense of what it looks like. It's the L2 is similar as the JWST, and there is 1.5 million kilometer away from the Earth. And see our telescope, and sorry, I put some Chinese words here, but show the main component. The key, this one is the antenna array. So they're allowed to download data every day. We don't have to move. It's an antenna array. That's very important. And here we point to the, Kepler, field. You can see, of course, every node, and, if it happen to be, there's astronomical planets transit, on the year base, every year you see once. And the other reason we monitor Kepler is because Kepler has the data. So we can take advantage of the data together, so therefore we can increase the signal ratio quickly. So therefore, if we find another Earth quickly with the Kepler data, we should, give a lot of credit to Kepler as well. So therefore, there is a really important one to do things together. And here's the macro lensing. You can see here, and you can see we basically, if they have free floating Earth, and of course the magnification is different time, so you can see the activity, the flux change differently from ground and space. So therefore, we can use that to measure the mass. That's one of the key things, because free floating planets, mostly they're just able to measure the events, but not mass ratio, but not mass. But here, hopefully we can monitor, we can measure 1/3 of the 1/3 to 1/4 of the those macro lensing planets with mass. So that will allow us to eventually detect the Earth mass planet. So that could be important. And here show you actually you can see here, this is our the real Kepler discovery, and here's our prediction in the Kepler field, and here's the macro lensing. You can see here in the cold side, galaxy center, so we can detect a lot of small planets, okay, and through this method. And here show you the everyone probably know this one. In the 1992, started with two of the planets around pulsar. And then of course, once this is kicked, 95, is a milestone, with the first planet around solar type star. And early on is all the radial velocity until 2000, and until David actually found the first transit, right? But in terms of transit method itself is 2002, I think. But initially the ground-based transit only can do giant planet. And but until 2009, you see the Kepler when they launched, and they are they see the planets really occupy these regions, super sublepton, and they are getting very, very close actually. If the Kepler allowed to have another 4 years extension, probably I'm not stay here to talk to you guys about us 2.0 mission. But unfortunately, and here 2008 is here, 28 our mission. Once we launched. Over 4 years, we'll quickly occupy these regions, while macro lensing occupy the this cold side and the free floating side as well. So this is our goal. We want to use this mission. Eventually, we can find maybe on order about 40,000 new planets, including about over 4,000 terrestrial size planets. That's very important because that's big population allow us to study this population. Just like Kepler found over 2,000 supers and sublepton. So you start that population. So hopefully this mission allow us to study this terrestrial planets population as well. So you can see here, and of course we'll go to find 10 Earth mass planet, Earth 2.0, and hopefully we can precisely determine the Earth 2.0 occurrence rate. And Mark is not here, but hopefully we'll able to help HWO to decide is 6-meter telescope or 8-meter telescope, right, with this occurrence rate. And then we hopefully will find free flowing planet as well. So we'll answer these key questions. Since my time is short, so I'll just stop here quickly. And here they show you that once we have the Earth-like planets, of course we'll do follow-up, and we do this simulation. If with the current parcel kind of radial velocity, put onto the GDC, which they have the plan. Actually, China is building the parcel type of instrument on the GDC. So with 30 magnitude, with the current parcel performance, we should able to over 2 to 3 years, we should able to confirm the Earth mass around 30 magnitude. That is typical magnitude. We will find Earth 2.0. Of course, we have some bright one could be 11, 12 magnitude. But the dominant one will be around 30 magnitude. That just show you that that's with 10 meters possible. Then with JWT, obviously, we can for bright one, we can do the atmosphere, and so therefore we can put all these work together. Eventually allow us to do the these kind of correlation to hopefully we'll find another Earth. And here show you the JWT really did a wonderful job. You see the JWT with Hubble with GDC. Now they already got this the TRAPPIST 1B and 1C seem to be they have fishiness and they maybe don't have atmosphere. So so that's indicated the telescope is very sensitive. Hopefully we're lucky we found some bright one. Maybe JWT can help us to characterize some of the atmosphere. And here show you the schedule. And in case you care about our mission, because it's rapidly developed. We starting from 2000 and now we are in the phase B. And we just start from this year, the beginning, January 1st, you know, phase B, and we will finish phase B by middle of next year. Then we're starting cutting metals, doing the engineering version. And by 2026, we're starting to the final version, you know, of the spacecraft. And we'll plan to launch it 2028, in middle of 2028. So it's a tight schedule, but seems to be we're on schedule right now. And here show you just the takeaway about summary. And in order to find another Earth with the transit, obviously the ultra high precision is really absolutely essential. And the instrument noise is really, as we see the Kepler show that, you know, is really can destroy the signal. So therefore we have to control the instrument systematics, and the activity is also another killer. So we have to be careful with that. So all these factors together, you know, we are doing that. Probably we eventually will reach our goal, you know, to find another Earth and to determine the Earth 2.0 occurrence rate. Thank you.
Thank you. Very interesting project. You had a lot of comparisons with the past Kepler mission, but what if you compare with the forthcoming ESA Plato mission that is to be launched just over 2 years from now?
Yeah. So the reason I didn't put that is because it's not real mission, and they don't have the official publication. We just use some data. We show that the Plato mission really designed for bright objects. They bright to 11 magnitude. And we are not a direct comparison. So therefore, we are pushing for, you know, to the 14 magnitude. So therefore, they are targeted very bright objects. So therefore, in terms of the, you know, sensitivity in the same field of view, we can, you know, target many more stars in the same field of view. So therefore, we are complementary to each other. So they are targeted more like a similar as a test for bright targets, but not for faint targets. When they go beyond 11 magnitude, they pretty much reach, you know, like detect noise. So we are not, you know, because of the, you know, the design and it's better the detector we choose is very low radar noise. So.
Just ask my own question then. You're targeting 2 million planets. You mentioned 25,000 interesting host stars at least for Earth 2.0.
Yes.
To find 10 Earth planets. I imagine that involves a lot of follow-up.
Yes.
Do you have infrastructure to do that much follow-up?
That's a very good question. Actually, I didn't got time to talk more. And in fact, first of all, you know, we are building our science team, you know, so therefore just like Kepler, like a test, we welcome all international people to join. In fact, we even have some NASA scientists, you know, as you know, joining as science interest. So therefore, we open to everybody, and if people willing to join, and we actually have the white paper, you know, we next year, I said next year, because why we didn't publish the final white paper, because we are waiting for the phase B to finish the final detail design. So therefore, we have the real mission, you know, everything fixed. So therefore, the science people, they can join. And from, you know, we have steady, every time we have people come to us to join the mission. So there could be help all kinds of things. The follow-up is the one we definitely have to be considered. You know, for example, like you point out, one of the keys is the radio velocity, and we will collaborate with Spain, you know, on GDC. And the other good news is China now actually have the money built 14.5 meter telescope right now. So we are also planning to build a high resolution spectrograph put on that telescope as well. But that is alone is not enough. Like you know, like David and many people mentioned, you know, you need a nodal telescope follow-up. So therefore, indeed, by the way, one thing I haven't mentioned, you know, our play scale is about similar to Kepler. Kepler is 4 oxygen per pixel. We have 4.8 oxygen per pixel, but still you have not four signals. You need a follow-up. You need a high precision, high photometry, and high contrast imaging as well. And the other thing we also want to point out, China, you probably know, they have the CSST. There's 2 meter onto the space station. So that is, give the contrast imaging is about 0.5 arcsecond, 0.15 arcsecond. So that can help as well. So therefore, we try to use lot of things for the follow-up. So therefore, we are open for the science and also open for the collaboration or follow-up as well. Okay.
Hi, yes, thank you. I was just wondering if you could speak a little bit more about why it is such a challenge to find these planets with this radius. Can you talk a little bit more about the main reasons you think there is just such a difficulty when it comes to that size? Yeah, I think there was an earlier.
Well, that's a very good question. Actually, if you look at the error budget, I don't have time to talk detail, but really the one thing you probably know is and here, of course, is stellar noise. Stellar noise is really is really dominant. Stellar noise is like if you look at the sun, the Kepler show only 1/3 of star, with noise less than 17 ppm. So therefore, that's why we want to use NAMOS to select those quite fine quite star. But on the other hand, the stellar, star, actually the Kepler give us a lot of lessons. Kepler, for example, didn't control temperature. So the imaging getting breeze, getting big and small. So therefore we do a lot of temperature control here to keep the instrument noise. I don't have time to talk detail, but you can see the lot of things matter in the end. So we have to do very careful with all those, eventually make the better sensitivity. Okay, thank you.
All right, so our next speaker is Lisa Krause. Welcome.
Hi, everybody. I guess it's customary to thank the organizers for letting one speak, but actually the thrill this time is that the astronomy community has actually come to Cape Town. So thank you all for being here. It's really exciting for us to have you all here. All right, so I'm going to talk a little bit about a project that's been ongoing for a number of years now at SALT, Southern African Large Telescope, trying to equip our telescope for precision radial velocity science. I don't think we need to convince anyone in this room that exoplanets are fascinating, and so this is where we're trying to head. Okay. All right, so just a little bit about SALT. So it's the largest single optical telescope in the Southern Hemisphere. And it's owned by a consortium of international partners. It's actually a near carbon copy of the Hobby Everly telescope in West Texas at McDonald Observatory. So the unusual thing about it is it's a fixed elevation telescope with a spherical primary mirror array, 91 individual 1 meter segments. And then the kind of complicated business end of the telescope is up at prime focus, where we have this tracker assembly that follows the image along the focal surface. All right, so it's kind of amazing for a country like South Africa to have one of the biggest telescopes in the world. It's because of this novel design, which gives you 70% of the sky at 20% of the cost of a conventional fully steerable telescope. But because of the way it works, it needs to be fully Q scheduled. And so we have observing teams that take all of the data and send the data to the PIs the next day. All right, so we have 3 spectrographs now, a versatile prime focus imaging spectrograph, the RSS, a fiber-fed HRS, and most recently a near-infrared IFU, fiber IFU. But what we want to do is we're obviously looking to grow the partnership to fund future developments. And so an obvious thing to pursue would be exoplanet science. All right, so how do we do that? Well, perhaps we need to build a dedicated instrument for that. Or perhaps we could tune up our HRS and get it good to go to play exoplanets. All right, so we've had the instrument now for 10 years. And before it was completed, it was actually built by Durham University Center for Advanced Instrumentation. We sort of slipped in the requirement, can you put in a mode that could maybe make provision for exoplanets? So they did throw in an iodine cell, and they did throw in a simultaneous thorium-argon feed, along with a fiber double scrambler. So kind of the bones are there, but now we have not had this in our user community yet. And so we've needed to basically commission this mode and get it going for what we need. All right, so this is just a very sort of noisy, whoops, how do we go back? Oh. How do we go backwards here? Oh. The red one. Ah, okay. All right. Back right up. Okay, so where is our laser? There we go. So just a complicated flow chart of the different options to consider, whether we're going for a new spectrograph or whether we could use either the iodine cell or the simultaneous thorium argon and potentially add a laser comb if we think the instrument's really up for it. All right, so this is just a little bit about our HRS, affectionately known as her Royal Spectrographness. It's a 2-channel vacuum shell. You can see the tank over here, filled with all these beautiful optics. So it's the 2 channels, red and blue, with a split at 555 nanometers. It has 4 modes. LR and MR use 500 micron fibers, unsliced and sliced. And then the high resolution and the high stability modes use 350 micron fibers sliced 3 ways. So the high stability mode is the bit that was designed for precision radial velocity work. And the picture down here shows this little bench that's just outside the vacuum tank. And basically you've just got, so the fibers come in from the telescope down here. There's a gap in the middle, and then they go off into the spectrograph here. And there's a linear stage that can drive various little stations along to either position the iodine cell or the thorium argon feed, or potentially a laser frequency comb to feed into the instrument. All right, so first thing we decided to do was try out the iodine cell. So some painful lessons learned here. Turns out these commercial cells are no good. There's a huge blob of iodine in there, and that's actually just really not fit for purpose. And so in the end, we contacted Paul Butler, the guy who actually invented these things, got him to come out and help us. We bought one of his cells from him. This is it down here compared to the commercial cell. We need to get it calibrated at very high resolution using a Fourier transform spectrograph with a resolving power of 1 million. So that's being done over here at NIST. And then we got Paul to come out and basically talk to us about how all this works, teach us about it, reduce the data. And so we did observe a bunch of stable stars. We managed to push down below 10 meters per second. But unfortunately, we added on the iodine cell when the optical design was already fixed. And so we end up with the dichroic split of the instrument being right in the middle of the range of the iodine cell. Too bad. Okay. But anyway, it was a blast. We loved working with Paul. He's amazing. But it was time to move on to the simultaneous thorium argon. But obviously keep the contact. All right. So if we just go back, and we just look at up here, we added a little station that includes a 50-50 beam splitter and a fold mirror so that we could simultaneously feed the thorium argon light down both fibers and do some stability tests to see how the instrument performs. Basically just to check that the fibers really do fly information as they should, given that the whole thing is in a vacuum tank. But we didn't want to just go ahead and make a huge investment without really verifying that the instrument's up for bigger things. So we did those tests. But really in the back of our minds all along, the state of the art for this business is really the laser frequency combs. And so we wanted to first just check out whether that's going to be viable. All right, so laser comb is basically just the pulse laser, an assortment of optical and electronic components that generates a wonderful array of stable spectral features with very precisely known wavelengths, equally spaced in frequency that can span. In our case, we just wanted to look after the red channel of HRS because that's where the argon lines and the thorium argon lamp totally hose the detector, and it's just very difficult to work with. The blue channel is okay, but the red channel, we were sort of eyeing out a frequency comb. All right, so just a nice analogy for how to think of a laser comb. Basically, how much better you can do describing a color of something if instead of just using red, green, blue, you can use much more descriptive terms. So you can see over here, stellar spectrum, there's one thorium argon line. Here's a laser comb with a multitude of very precisely known known wavelengths. All right, so back in late 2015, we were contacted by these guys from Heriot-Watt University in Edinburgh. They'd actually contacted the guys at Durham and said, you know, anyone with a high resolution spectrograph that would want to play with a laser cone. It seemed like something way too good to be true, so we said yes. And so you can see they basically compressed their normal lab's worth of laser cone, put it on a small bench that could be shipped on a shipping pallet, sent it to us, and we got this going at SALT. And they left it with us for about 3 months. So that was extremely good fun, fascinating exercise for all of us. They'd never played with a big telescope. We'd never played with a laser comb. So very, very exciting. And what you can see down here is a red channel image with the thorium argon light down the one fiber and the laser comb light injected down the other. So you can see just how much better the laser comb is compared to the thorium argon. All right, so fast forward a few years, we finally managed to get funding that we'd be able to contract them to build one of these for us. But we talked about it and realized really to just buy a black box that, you know, we wouldn't necessarily be able to maintain very well. And we just wouldn't learn very much about it. We said, how about instead of we build the components, you build it and send it to us, what if we buy the components, ship them to Cape Town, and we fly the people around instead? So instead of these fragile components that could easily get damaged, we got them all to Cape Town. And here you can see Richard in our lab in Cape Town with a bunch of our interns and our engineers. So the idea was, it's not as efficient to build it this way, but it's a wonderful opportunity for us all to work together and get to learn about this thing from the ground up. So that's what we're doing. Probably don't have time to go through this, but just super quick, just the main elements of the comb. You need the titanium sapphire femtosecond pulse laser, the tube mode lock. It produces a 2-watt beam at 800 nanometers. So you can see over here, the mode lock laser produces all of these frequencies. In order to make it useful for an astrocomb, you need to broaden that with a photonic crystal fiber, an amazing little device, which is about a 2 micron diameter fiber that has air gaps within it. So it's an extremely complex structure that when it interacts with this powerful laser, produces this supercontinuum of lines of these different modes. You then need to thin that out because it's too dense for the spectrograph. And so you have a Fabry-Perot cavity that thins out 19 out of every 20 of these modes. And then you do some spectral flattening and you feed the whole lot into your spectrograph. Sounds pretty simple, but a lot of the devils are in the details. All of these little boxes with red around them, those are the electronic locking loops that basically keep everything stable and control the system. But okay, here it is. This was back in April, May, up at SALT. This was I think their 3rd visit to the telescope, putting it all together. It's not going to look like this long term. This was just kind of the maximum chaos phase just before we got engineering first light, just getting all of the bits together and working. So this is Richard and Shan, his postdoc, who have been doing all this work. The other cool thing is this unit here, the SIAO in Cape Town has a fantastic mechanical workshop. We actually got to make the comb chassis for this thing. So there's actually a bit of homegrown stuff as well. Also some of these electronics boxes, our engineers up at SALT were given, designs for what's needed and they've put that together. So it really is a collective effort here. So here we are getting first light. This was very exciting. So 5th of May, we managed to get comb light down both fibers. So there's the image. And then a few nights later, just at the end of their week, we managed to get a radial velocity standard star injected down the one fiber and the operational comb into the other. And so you can see the comparison here. Very exciting for them. They're not used to getting to see their laser lab stuff sitting next to a stellar spectrum. Here's a little extraction that shows the H alpha line, and all of these blue features are the individual comb teeth that would be used to calibrate it. This is just a quick on-the-fly reduction, but you can see where it's going. Just a nice comparison of how much better the comb lines are compared to the sparse thorium-argon lines that are often blended or too faint or too sparse. So down here you can see the sort of thicket of comb teeth versus the one individual thorium-argon line in that order. This shot over here shows injecting the comb lines that comes through from next door through the single mode fiber, hits a beam splitter, and then goes into spectrograph there. So obviously the hardware is one thing, but the other critical part of all this is the data reduction pipeline. And so that's been in progress as well. So being written in Python, we used it obviously to do these stability test runs to try to figure out how stable the instrument is. We've also been taking some data of a known exoplanet system just to test the code as it stands now. We also, of course, don't have the complete comb yet. We have one more thing coming up, and one more run coming up to complete it, and then we just need to finish the pipeline and get going. So this was not a very ambitious system. We just recovered something with an amplitude of about 30 meters per second, but at least, you know, as a first attempt, it's a factor of 10 improvement from what our nominal pipeline does. All right, so there's our remaining steps, but yeah, we're having fun, and hopefully we'll get this going pretty soon.
So the next speaker is Dr. Stefano Bellotti.
Yep. All right. Hello, everybody. My name is Stefano Bellotti, and I'm a postdoc researcher at Leiden Observatory. And first of all, thank you very much to the organizers for the opportunity to present my work, which is going to be about characterizing the space environment of known exoplanet hosts. And in particular, I'm going to focus on two of them, GJ436 and HD 63433. A little bit of motivation / background for this. Which one is it? Is it the red one? Oh, the green one. But that's the blazer. Oh, sorry. Oh my God. Okay. Let's see. Okay, sorry. Yes, a little bit of motivation. Well, I don't have to go too much into detail because of Dominic's talk before, but stellar magnetism and activity is responsible for heterogeneities on stellar surfaces, which hinder our capability of detecting, but also at characterizing exoplanets in terms of atmospheric retrievals, but also in terms of chemical composition. But they're also important in terms of star-planet interactions. Yes, because the magnetic field of stars dominates and regulates the environment in which these exoplanets are embedded, and therefore for the interpretation of data, and we need to understand better what is going on pretty much. Now, the way we detect and characterize stellar magnetic fields is via a specific observational technique called spectropolarimetry. Basically, it is based on the Zeeman effect. So what happens to atoms and molecules when they are immersed in an external magnetic field. In that case, the energy transitions split, and consequently, we have more energy transitions and therefore more absorption lines. And these new, this family of new transitions have different polarization properties. So if we take high resolution spectra or in circular polarization or linear polarization, we can basically infer the properties of the magnetic field. But because we are dealing with source-like point-like sources, and therefore disk integrating quantities, we will not be able to, we will not be sensitive to the small scales, but rather on the large scales. Okay. So we're going to deal with the large scale magnetic fields instead. And in particular, the way we reconstruct the magnetic field is via a tomographic inversion technique called Zeeman Doppler imaging. What we want basically is a time series of, in this case, a circular polarization spectra from which that sample the rotation of the star. Because in that way, we are basically sampling the orientation of the magnetic field vector as the star rotates, so that we can invert it back into a map. This particular GIF is an academic case. We're not going to have this kind of spatial resolution, but this was to show pretty much the correlation between a radial magnetic field patch and the corresponding evolution of the polarization signature as the star rotates. Now, okay, so this work is basically, this work I'm conducting is basically in preparation of the aerial mission for the characterization of thousands of exoplanets' atmospheres. But it finds also interest and motivation in more general, like also for JWST or more generally for exoplanetology, because as I said at the beginning, we want to understand the environment in which these exoplanets are embedded. So the campaign I'm conducting is basically divided in three parts. One dedicated to understand whether the magnetic field of a star is detectable. The second part, upon success of the first phase, is to reconstruct the magnetic field of the star for the first time, and eventually the stellar environment in which the exoplanet is embedded. And then on the long term, what we want to see is to reconstruct basically the magnetic field of stars multiple times over perhaps a yearly timescale in order to see the evolution of the fields and potentially trace magnetic cycles, which would be key for observing for observational strategies for these missions. Now, at the beginning, I said that I was going to talk about GJ436 and another star. So here I'm summarizing a few fun facts about the star. It's an old M dwarf rotating slowly around 44 days, and it has Neptune-like planet around it that is outgassing, and because of the interaction with the stellar wind. And this is famous because it has a trail that looks like a comet, and it is basically visible when the planet is transiting the star. Now, what we did was to reconstruct the magnetic field of the star, shown here on the left. This is basically a simple dipole. It's a little bit tilted, but with a strength of 16 Gauss. So if it probably that tells you nothing, but in comparison to the sun, the large-scale magnetic field of the sun is 1 Gauss. So this is 16 times stronger, for instance. And the blue polarity, the blue color indicates the negative polarity, and the red color indicates the positive polarity. So we have a dipole. We fit this into magnetohydrodynamical models of the stellar wind, and we obtain these results. The star here is at the center, and the streamlines indicate this, the extrapolated magnetic field. The orbit of the planet is shown here with this circle, and then this irregular shape is the Alfvén surface. It's basically it indicates where inertial forces dominate with respect to magnetic forces. So inside of this surface, basically in the subalvenic regime, the magnetic forces dominate, and therefore we have certain kind of interactions between the star and the planet. In particular, we can have certain connectivity between the eventually planetary magnetic field and the stellar magnetic field. So as we can see here, for instance, our results show that the orbit is fully subalvenic. And when we go into a little bit more detail and we look at the properties of the stellar wind at the planetary orbit, this is what we obtain. On the y-axis, we have different properties of the of the stellar wind, such as ion density, wind velocity, magnetic field. On the x-axis, instead, we have time. We have 44 days, which is 1 stellar rotation. And these spikes that we see in these properties, it's because of the planet orbiting around the star. And in particular, because the planetary orbit is polar. which means that the planet is encountering over the course of an orbit both open magnetic field lines and closed magnetic field lines. So it's encountering different environmental conditions. At the same time, we have some, so we tried two models basically. That's why we have dashed lines and solid lines. And the solid lines pretty much reproduce better the observations that are shown here as crosses in this plot. And so basically the takeaway from this is that, well, our model reproduced the observations, yes, but especially the fact that there are significant variations over the course of an orbit. Now, if we go to the other star, which is HD 63433, this is a different type of star. It's a young solar-like active star with a rotation period of 6.5 days, pretty much. So it rotates around 4 to 5 times faster than the sun. And around this star, there were 2 planets were discovered. And atmospheric studies showed that pretty much only the outward planet had, well, kind of retained a primordial hydrogen-helium atmosphere, but it's still outgassing, whereas the inner planet probably lost it. So they have different atmospheric evolution pathways, which is why it's interesting to study the system. And then more recently, another planet was found in the innermost planet. It's hotter. It's Earth. It's Earth-like in the sense that it has the same size as the Earth, pretty much. And it was assumed that because the planet B doesn't have an atmosphere, most like a primordial atmosphere, most likely also planet D doesn't have it. So what we're interested in, though, here is the environment. Again, we used the same pipeline, we used the same formula pretty much in the sense that we recovered the magnetic field map at first. In this case, as we can see, it is a complex magnetic field, which is consistent with what we know for young stars, especially solar-like. And then we reconstructed the magnetic field. In this case, we had to zoom out, let's say, because the planets are more distant from the star with respect compared to the previous case. But pretty much, yes, we see that perhaps only the innermost planet is within the Alphen surface, where certain magnetic interactions can occur. And this is indeed what we find. This is the Alphen Mach number over the stellar rotation phase. The Alphen Mach number is pretty much telling us where the Alphen surface is. A value of 1 is the surface. So below that value, we are in the subalvenic regime, which is what we see for planet D for about 12% of its orbit. It means that it encounters only for a little fraction of its orbit this regime. Whereas for the other planets, we have different kind of orbits in the sense that they are outside of this surface. So I'm going to pretty much summarize what I said. Basically, we're trying to study the stellar environment of known exoplanet hosts. And I've shown 2 different scenarios. One where the planet is within a surface where the magnetic interactions with the star can occur. And so there could be some connectivity with the star and therefore certain kind of interactions. Whereas for the other stars, apart from this 12% of the orbit of the innermost planets, the other ones are outside. They are in the superalvenic regime, as the solar system planets are. So we can expect something like bow shocks between the stellar wind and the magnetosphere of these planets, if they have any. And in terms of prospects for this work, what we want to do is to extend the sample of stars over which we are performing these studies to get basically the magnetic map and the stellar wind environment. But we also want to keep monitoring these stars in particular to see how both the magnetic field and the environment is going to change if cycles are there, basically. So with that, I'll stop here and thank you very much for the attention.
I just want to point out that the magnetic fields that you're citing, of course, are spatially averaged, and the fields, of course, since it's circular polarization, they cancel each other out. And typical magnetic fields would be on the order of a kilogauss.
Yes.
But for calculations of stellar winds, it's the large scale field that's important, as
Precisely.
you pointed out.
Yeah, and in particular, what I was showing, it was the radial component of the magnetic field, which is the most important component for the wind modeling, but that's correct, yes. Thank you.
So our next speaker is Rena Lee. All right, hi everyone. Thank you all for attending my talk, and thank you so much to the organizers for selecting me to share my work. My name's Rena. I just advanced to candidacy in the PhD program at the University of Hawaii at Manoa. And I'm here to share with you the first results of my dissertation work. So I'm pinning down the masses of extreme Earth-sized planets as prospective targets for JWST. So let's get into it. So I'll start off with this snapshot of all 5,600 plus confirmed exoplanets to date. This is quite an accomplishment by our field so far. Well, you'll notice that there's quite a dearth of Earth-sized planets still, especially the true Earth analogs. So we're probably not that far off according to the Earth 2.0 team, a couple of years off. So detecting true Earth analogs is at or beyond the observational limit of the current leading spectrographs in photometry. However, much shorter period Earths imposing RV semi-amplitudes of about an order of magnitude larger are now routinely detectable, which is what I'm doing for my dissertation project. So in doing so, fill out some of that underpopulated parameter space to possibly reveal new trends in this snapshot of the exoplanet population. So some background on those planets. So-called ultra-short period planets are defined as planets on extremely short orbits of less than a day and almost never exceed 2 Earth radii. So because of their extreme orbits, they are so strongly irradiated that any primordial atmospheres are expected to be completely stripped. And their equilibrium temperatures typically range from around 1,000 to 2,000 Kelvin. So the hotter end of these are nicknamed lava worlds, as we've heard about in the session today. And so far, about 200 USPs have been discovered, and their occurrence rate around sun-like stars has been estimated to be about 0.5%. However, only a couple dozen of these have had precise mass measurements to date. So here I've plotted in mass radius space the USPs with mass measurements in blue compared to other longer period Earths and super Earths in gray. And on average, they have smaller measurement uncertainties as their planetary signals are amplified due to their proximity to their host stars. So they impose larger RV semi-amplitudes and their transit signals are also greater. And because they lack thick primordial hydrogen or helium envelopes, precise mass and radius measurements alone can allow us to directly probe their interior compositions as well, lifting that degeneracy. So for super Earths, we expect planets to follow a roughly Earth-like composition. So planets that are larger than about 1.8 Earth, larger than 1 Earth radius, to follow a roughly Earth-like composition due to giant impacts, which I'll delve into a bit later. However, for smaller bodies less than about 1 Earth radius, there may be a larger diversity of compositions if they have undergone fewer collisions by way of small number statistics. And we can actually see this in our own solar system. So these are the core mass fractions of the terrestrial planets, Mercury, Venus, Earth, and Mars. And while most of them are fairly consistent at around a roughly 30% iron core, which is also roughly consistent with that of the carbonaceous chondrite meteorites and the composition of the solar photosphere, Mercury is quite anomalous at 74%. So let's briefly go over how this may be. So the pebble accretion model of planet formation theory posits that a protoplanetary disk, in the protoplanetary disk, pebbles of around centimeter to millimeters, or to meter size, my bad, begin to aggregate due to interactions and drag from the gas in the disk. And this process acts, if this process acts alone and is efficient enough to build Earth mass and larger planets, then the planet compositions should directly reflect the disk and therefore the stellar composition. However, traditional planet formation theory posits that planet accretion, pebble accretion only takes the process so far, and that the final assembly is done by way of giant impacts.
So instead of planet-sized bodies post-dissipation, we get lunar-sized bodies about a tenth the size of the Earth that undergo a series of collisions that builds up planets into their final forms. And of course, different types of collisions, depending on the mass ratios of the colliding bodies, the velocities, the different impact geometries, can have drastically different outcomes, altering the planetesimal core mass fractions. Rocky mantles of smaller bodies, for example, could be completely stripped in catastrophic mergers and hit and runs. However, collisions are stochastic, and the final CMF of a planet is the outcome of many different collisions. And simulations show that after a sufficient number of giant impacts, compositions tend to average back to their starting point, especially for larger than Earth's mass planets. However, as I mentioned earlier, this may be mass dependent, so smaller bodies statistically may undergo fewer collisions, leading to a wider diversity of CMFs, leading to amongst the Earth and sub-Earths. Oops. So getting into my first results, here are the stellar parameters of my first system, a USP system, TOI 6324. So the host star is a nearby mid-M dwarf that we characterized with empirical spectral matching and direct isochrone modeling. And TOI 6324 was observed by TESS for 5 sectors. We removed spurious data points and detrended the data using a spline fit in the Wotan Python package, then employed the exoplanet package and PyMC3 to perform a transit fit, and we find a radius of just around 1 Earth radius for TOI 6324b. For the mass measurement, I have been fortunate to have access to the newly commissioned Keck Planet Finder situated at Mauna Kea Observatories as a member of the California Planet Search based in Caltech and as a student at the University of Hawaii. So KPF is a high-resolution optical fiber-fed shell spectrograph with a target RV precision of around 30 centimeters per second. And we've attained 85 RV measurements of TOI 6324b over the course of our survey. And in the early commissioning days of KPF, we were experiencing some thermal drift in the instrument leading to some correlated noise, as you can see in the raw data in the top left panel. So to mitigate this, we employed a Gaussian process model with a squared exponential kernel to model out this long-term trend. And we could recover a remarkable RV curve corresponding to a semi-amplitude of 2.85 meters per second, or a mass of 1.23 Earth masses. And as an independent check to the GP model, since a lot of times these GP models can overfit the correlated noise, another common strategy for dealing with correlated noise in short period RV data sets is the floating chunk method. So because of the sub-day orbital period, we can discard information about the radial velocity variations between nights and focus on intra-night variations. So in essence, any long-term stellar variability or activity and instrumental effects are removed by allowing each night to have an independent additive RV offset. So the raw data in the top left panel, and then the offset minus the offset in the lower left panel. We find a consistent result to the GP fit within 1 sigma there. And because the GP model has far fewer parameters without all the individual nightly offsets, we adopt the GP results for the rest of this analysis. So here is TOI 6324b on the mass radius diagram plotted in red, and unsurprisingly, it is very similar to the Earth-like composition as with the other USPs, and the plan is to continue measuring the masses of USP candidates as well as revisiting previously confirmed USPs to understand the distribution of compositions in this mass regime. So we'll also be revising some other previously confirmed USP systems in order to better get a better picture of this distribution. And a step beyond a simple mass radius relation, I've modeled the core mass fraction of TOI 6324b by numerically solving the interior structure of the planet based on the equation of state extrapolated from the Earth's seismic density profile. And we find a core mass fraction of around 56%, so a bit higher than what we've seen within our solar system. So with these core mass fractions, we can begin to test the mass dependence of giant impact theory. So on the left, we have the results of giant impact simulations adapted from Skora et al. 2022. wherein they allowed a bunch of planetesimals of lunar size to undergo a giant impact phase. The resulting planetary masses after a certain number of collisions in the color scale are plotted, and their resulting core mass fractions on the y-axis. We can see that for the super Earths of mass greater than about 1.8 Earth masses, most simulated planets converge back down to a roughly Earth-like composition of 0.3 or 0.35 core mass fraction. However, for the smaller bodies of less than 1.8 Earth mass, we find a larger diversity. In the observed exoplanet population so far, while we observe quite a diversity amongst the super Earths as well, if we take a binned average of what has been observed so far, because the measured core mass fractions are so uncertain due to the presence of atmospheres or other measurement uncertainties, we do find that the core mass fraction is roughly consistent with that of an Earth-like composition. However, for the Earth-size planet mass bin, it's quite underpopulated, and the jury's still out in that region, other than the TRAPPIST planets, of course. And with our revised GJ367 result and TOI 6324b, we're finding a roughly consistent CMF binned average so far. But as I said, this is a very preliminary result with not enough sample. So of course, simple mass and radius measurements can only take us so far. And to further characterize these extreme Earths, we can turn to JWST. So one key observation is the phase curve, which traces the planet's brightness as a function of its orbital phase. And another is the emission spectrum, or the spectrum during secondary eclipse. So here I've simulated the phase curve of TOI 6324b using Pendexo for an observation with MIRI. And as Dave Charbonneau mentioned in his Kavli talk earlier, many of these M-dwarf terrestrial planets aren't really expected to retain their atmospheres, perhaps due to stellar activity, and USPs perhaps especially so since they're so hot. But with just 3 phase curves, we would be able to constrain the bare rock surface of these types of planets. And in the absence of a high mean molecular weight secondary atmosphere, an emission spectrum would allow us to directly probe the surface mineralogy of the planet. So I won't get too much into the atmospheric details, since we heard a lot about that today, and I'll focus a little bit more on the surface mineralogy and geology. So basaltic rocks, often referred to as secondary crust on the Earth, are typically formed by volcanic eruptions of low viscosity lava. And sustained volcanic activity may be constantly producing a basaltic surface before space weather pulverizes it. While on the other hand, granitoids are more akin to modern day continental crust on the Earth, and it emerges from extensive reprocessing of silicate rock by plate tectonics with the help of water. So basalts, which are richer in iron and magnesium, are typically darker. A basaltic surface is hotter and gives a stronger thermal emission overall. So that's the red simulated spectrum. And another distinguishing spectral feature is the absorption of the silicate oxygen bond, a stretching mode at around 8 to 10 microns. The dip, the dip right here. So a granitoid with its higher silica content exhibits more pronounced absorption in this spectral band than the basalts would. And a secondary eclipse would allow us to distinguish between these two. So a quick note, because of their extreme orbits and because of tidal locking, USPs are expected to be tidally deformed. And so observing the phase curve, while it might not reveal an atmosphere, may actually allow us to measure the effect of the tidal distortion as we observe different disk geometries over the course of the planet's orbit. So to quickly show the feasibility of these observations here, I've highlighted TOI 6324b, as well as a couple other USPs in my sample that I'm working to confirm, with the highest emission spectroscopy metrics amongst Earth-sized planets, as well as other selected JWST targets. And to summarize, just zooming back out, we're just pinning down the masses of the smallest, most extreme Earths to inform the final stages and the mass dependence of giant impact theory. And by confirming these systems, we aim to target these with JWST observations to further explore their surface mineralogies and geological evolution. So just some closing notes. This work will be submitted very soon, so please do not share until you see it on the archive in the coming weeks. Thank you again for your time and attention. And if anything, if you'd like to discuss anything I've mentioned here in more detail, I'm happy to chat over email. Thank you.
Tom Green, NASA Ames. It's exciting to be able to start to characterize the surfaces of these planets. There's also a paper about to be accepted on looking at TRAPPIST-1b in 2 different thermal bands. And a little surprisingly, it looks rather ultramafic.
Okay, super cool. Thank you.
All right, thank you. There's been a little bit of a change of plan here. Our last speaker instead will be Mr. Jeffrey Linsky, professor, I should say, sorry.
Hey, I'd like to thank the organizers for allowing me to give this talk. A major theme of this meeting is the whole question of stellar noise and how it affects exoplanet atmospheres. And let's see if we can get this to go forward. No. The green button. Ah, okay. I wrote a book 5 years ago on the question of stellar noise and how it affects exoplanet atmospheres. A second edition will be published later this year. And what I'm going to talk about now is a subset of these issues. So what I'd like to do is talk about 2 very critical questions, namely, under what conditions can an exoplanet retain its atmosphere? And second, what is the chemical composition of an exoplanet's atmosphere as driven by photochemistry? The first question really is what's happening in terms of hydrodynamic mass loss. There are many ways in which an atmosphere can be eliminated by the star, but hydrodynamic mass loss is certainly a dominant mechanism, and that's driven by the extreme ultraviolet radiation from the star between 100 and 912 angstroms. The photochemistry is driven primarily by Lyman alpha at 1216 angstroms, which dominates the ultraviolet spectrum. And what's in common between these two, the EUV and the Lyman alpha, is most of it cannot be observed. Unfortunately, there's interstellar hydrogen in the interstellar medium, and that absorbs most of the EUV and most of the Lyman alpha. So what I'll talk about is how to reconstruct those 2 fundamental drivers of whether a planet can retain its atmosphere and its chemical composition. Okay, first, thermally driven mass loss. There are 2 extreme regimes. There's what's called the energy limited case, in which photons are absorbed, either photoionization or dissociation in the outer atmosphere of a planet. It produces heat, work against the gravitational pull of the planet, and therefore contributes to mass loss. In that case, the efficiency is 1, this parameter eta. The other extreme is recombination limited, in which a photon comes in, ionizes or photodissociates, followed by a photon being emitted in that process, and therefore no work against the gravitation of the planet. the efficiency is 0. It turns out this parameter eta is absolutely important for whether a planet can retain its atmosphere. And unfortunately, many studies assume a parameter like 0.15 for eta, but it depends really on the star. It depends on the spectral energy distribution of the star, depends on the age of the star. It's really a complicated part. So we know stars lose mass. Planets lose mass. They can be like comets. This is a tail as shown on the left in Lyman alpha. And that absorption, extra absorption seen in the red line on the right side follows the planet after it's passed across the star. There's mass loss. We know that. Okay, let's talk about the extreme ultraviolet spectrum. There's only one star in the universe for which we will ever observe the extreme ultraviolet spectrum in its entirety, and that's the sun. Okay? The extreme ultraviolet consists of 2 components. One component is chromospheric emission from a 10,000 degree plasma, and that's shown on the, let's see if I can get this right. Yes. The Lyman continuum, which is recombination of hydrogen, helium continuum, a number of emission lines here driven by the chromosphere, and then a whole bunch of very strong emission lines produced by million degree plasma. So that's corona. So whether a star, the extreme ultraviolet spectrum is dominated by the chromosphere or by the corona depends upon the star's activity. In the sun, in the solar case, it's primarily chromospheric. In the case of an M dwarf, typically, it'll be coronal. So on the right side of this diagram is the only observations we now have from a satellite of the extreme ultraviolet spectra of stars. This is the EUV-E satellite. And you'll notice emission lines going down to about 400 angstroms and nothing beyond. And the reason is interstellar hydrogen absorption. And that's shown on the left. It's plotted the optical depth in hydrogen as a function of wavelength. And you'll see it at about 40 nanometers, 400 angstroms. Essentially, you reach optical depth unity, in which case you see very little, if any, extreme ultraviolet radiation. So we have to reconstruct it. There are a number of techniques, and I'll go through a few of them. I list on this diagram. The simplest technique is, why not just compute a model atmosphere? It's not easy. Model atmospheres are pretty complicated. And the only test case we have is the sun. So what's shown on the left is a comparison of a computed solar spectrum. That's 13x1, computed by Juan von Tenla, and compare it against Eve and solstice, which are solar observations, and you can get a pretty good match. What's shown on the right is models of the sun at various levels of activity, in which case you see that the Lyman continuum, of course, gets much brighter with activity, but all these, at the shorter wavelengths, all these coronal emission lines dominate. So another technique is called differential emission measure analysis, which is just a fancy name for saying that you look at a given ionization stage, let's say iron 17. You look in the X-rays, you see an iron 17 line, which is typically optically thin. You then say, oh, that's produced by collisional excitation. You then say, well, there's an iron 17 line in the extreme ultraviolet, and then compute its flux from the X-rays. You can do this for many lines, and what you find is stars that are very active have a lot of emission at 10 to the 7 degrees, whereas the sun, most of the emission is around 1 million degrees. So that changes the spectral energy distribution in the extreme ultraviolet. And that's shown over here, namely, rotated. You'll have to rotate your eyes 90 degrees. But anyway, look over here. Comparison of the solar extreme ultraviolet radiation showing the chromospheric component and the coronal component. And now for this very active young star B1298 Tauri, what you see is essentially the coronal component totally dominates. So whether it's an active star or an inactive star, the spectral energy distribution that drives the mass loss from the exoplanet's atmosphere can be totally different. One size does not fit all. Okay. So another way is there a correlation between X-rays and extreme ultraviolet? X-rays can be observed. Various satellites do that. And there is indeed a correlation, but the correlation is not one-to-one. The slope in a log-log plot is not unity, it's different, which means that for inactive stars, let's go back one. How can we go back one? Okay. Inactive stars like the Sun, Alpha Centauri b, the extreme ultraviolet flux dominates over the X-rays, but for M dwarfs and active stars, the X-rays dominate over the extreme ultraviolet. So there's a very change in character as you go from inactive stars to active stars. Okay. Another technique is to measure the unsigned magnetic field. And it's thought that the magnetic field is what's responsible for high energy emission in stars. And the correlation is actually very good for the Sun, as shown on the left. And Reiner's published a paper in 2022 of M dwarfs showing there's actually a very good correlation for M dwarfs. So let's get a little bit more explicit. Let's start talking about M dwarfs. And what's shown here on the right is a comparison of the solar spectrum with the spectrum of TRAPPIST-1 normalized by the bolometric luminosities of the two stars. Okay? So when you do that, you find that as you go towards the optical, longer wavelengths, the Sun totally dominates. But as you go into the extreme ultraviolet, the two stars are equally bright on that scale. But in the extreme ultraviolet is where the essentially the cross sections of many important molecules are located. Okay, we're going to come to that when we talk about Lyman alpha. Okay, so what was done in this paper, I showed the author. Let me go back here. Okay, a very recent paper by Van Leeuwen, 2024. And what the authors have done is basically say, let's compute how long an atmosphere can survive in a planet as a function of the flux, extreme ultraviolet flux seen at the Earth, but multiplied by a multiplicative factor. So let's say one, maybe twice the EUV flux seen as the Earth, 14 times for a number of different chemical compositions, but mostly nitrogen and CO2. Okay? What happens to the atmospheres? What's shown here on this dashed line is the loss of an Earth-like atmosphere in 1 megayear, 1 million years. So when you get to 14 times the EUV flux as seen by the Earth, what you find is essentially the atmospheres are all, no matter what the chemical composition is, the atmospheres are totally lost in a million years. However, the TRAPPIST-1 planets all have fluxes that greatly exceed 14. Okay, so conclusion. all the TRAPPIST-1 planets are bare rocks. Sorry about that. Okay. In order for the TRAPPIST-1 planets to have an atmosphere that lasts more than 1 billion years, a giga-year, they have to lie out here. That distance, they actually lie much closer in. So let's take it one step further. Not only are the TRAPPIST-1 planets bare rocks, but probably most planets in the habitable zones of M dwarfs are bare rocks, unfortunately. Okay, so there are a lot of issues related to mass loss of exoplanets. I list them here, but let me very quickly talk about Lyman alpha. Lyman alpha is only seen completely in the sun. Interstellar hydrogen totally absorbs the whole core of the line. But fortunately, nature has been very kind to us and has given us the deuterium Lyman alpha line, which is this narrow feature just to 1/3 of an angstrom away from the hydrogen Lyman alpha line. Deuterium is 100,000 times less abundant than hydrogen. So hydrogen is totally optically thick, interstellar hydrogen, but deuterium is optically thin or almost optically thin. So we can reconstruct the hydrogen Lyman alpha line from the shape of the deuterium Lyman alpha line. Okay, I'm almost out of time, but let me just point out something, two things important. One is the, in this reconstruction process, the hydrogen Lyman alpha line flux is much, much larger than what is observed. And secondly, Lyman alpha totally dominates photo dissociation of important molecules. And what's shown in this graph is the cumulative photodissociation. In other words, as you go from the very shortest wavelengths to longer wavelengths, what you find for water is total photodissociation by Lyman alpha. Same thing with methane, and actually CO2 is similar. So I'll end at that point. Thank you.
Time for a quick question? Yeah, Jeff, really good talk. When you were going into the M stars, exterminate all atmospheres around them, have you looked to see, because we find there's a sweet spot as you move from the M6s towards the M3s and you put the planets sort of towards the outer edge of the habitable zone, it does look like there's a sweet spot. Have you found any evidence of that?
I've not explored the early M dwarfs, but my guess is there's a good chance that some of the early M dwarfs may retain an atmosphere or exoplanets in the habitable zone. But I do want to say the whole term habitable zone is, I think, a misnomer. It's habitable only in the sense of liquid water on the surface. It's not habitable in the sense of can organic material exist on the surface of the planet.